Hello, everyone. Welcome to day 2 of the first annual SU2 conference. I want to thank everyone that participated yesterday. We had a great session of talks. I think it was a really great day. And today we have a very similar setup for you. So we've got a list of featured talks as well as more lightning talks from our users and developers. And I just wanted to say the live stream from yesterday, you can find it on YouTube, on our YouTube channel. We'll also be posting that to the SU2 conference page. And the material and slides are also already available on the SU2 conference page from yesterday. So if you missed anything, everything's recorded. You can go find the PDFs there. But for today, I'd like to introduce our first speaker, who's going to take it away. So Tim Albring is one of our SU2 Foundation directors in charge of development. And so he's going to give us today a crash course for SU2 developers, a lot of great detail on how we use GitHub and develop an open source code. So Tim, as soon as you're ready, take it away.
Okay, thanks, Tom. Welcome, everybody. And yeah, like Tom already said, this is a crash course for SU2 developers. So let's get started. So you want to be an SU2 developer. If you can answer that question with yes, then welcome to this talk. And otherwise, maybe after that talk, you feel that you want to be one, because it's really easier than you might think. And the nice thing is that we leverage a lot of standard development processes and a lot of latest tools for open source projects, which means that you find a lot of material already available in the internet. So this is why I will just briefly have a disclaimer here for what this talk is not actually. If this slide works here. Let's see. Yes, okay. So let me give you a small disclaimer first what this talk is not. It's not a programming tutorial. It's not a guide on how to install and build SU2. It's not a source code walkthrough. It's not a professional software engineering lecture. Then furthermore, works here. Yeah, it's also not only for experienced developers, and it's not only for new developers, because we changed a lot of the processes over the last year or so. Yeah, so let's get started then with the topics. So usually as an SU2 developer, you will come in touch with 4 big topics. All of them somehow overlap, but I try to separate them in the course of this presentation. So first we'll hit the JIT branching. So this allows you to set up like a work environment where you can safely do your changes. The next step would be the development itself. I will give a brief introduction to the structure of the source code and the source code files. Then the third topic is how to open a pull request. So to let other people know about your changes and what you have planned during the course of your development. The fourth step is we want to make sure that nothing breaks when you add your changes. And therefore you have access to like a very extensive testing system. And then finally, hopefully, you'll have the release with your changes included. But let's start from the beginning. The first thing that you might ask is, where can I get the source code? And one obvious way of doing that would be to just click on clone and download here on GitHub and download the zip file. But this is actually not the way that we would recommend doing, because what we want to do is we want to track the changes in the source code files. And this is why we leverage a lot on the source code or version control system JIT. Which allows to easily revert changes or merge changes from others. Let's see whether that works here. Seems to be not working all the time. Okay. So what are JIT and GitHub? So JIT is a version control system that keeps track of your changes to the files over time. And like I said, that easily allows to revert your changes, merge changes from others. And GitHub is just a website that hosts like JIT repositories online. And repositories are just collections of tracked files. Each change made to the repository code is called a commit. And often, or like always, these commits should have like a supporting comment about what change actually was made. A typical GitHub workflow would look like the following. So you make some changes to your code, and then you add these changes to the staging area. Then after like a couple of changes that you made, you can just put them together in a commit. You commit these changes to your local repository. And then at some point you can say, okay, I want to make these changes public, and you can push them to the remote repository, which is hosted on GitHub. Then you can also fetch changes in the remote repository that were made by others. This can be done either by a JIT checkout or by a JIT merge. Okay. This is just a very brief introduction to JIT. And you might ask yourself, do I really need it? If you say yes, then just go ahead and install it. If you say no, then let me tell you, yes, you do. And you should also install it and use it. So if there is enough interest, then we can also offer an online course on that topic soon, which is of course then sponsored by the SU2 Foundation, which is also in line with our educational mission. And this actually holds true for all of the topics that I will cover now. So in case there is enough demand, we will offer separate courses on that.
Hey, Tim, just as a heads up, if you're having trouble with the slides, go ahead and just say next, and Juan can flip them, okay?
Yes, okay, thanks. Okay, this is just a quick overview on how JIT actually, a typical JIT workflow would look like. So all of these small dots here are single commits, and a branch is essentially a collection of all these commits here, or of several commits. In SU2, we have two main branches. So one is the master branch and one is the develop branch. In the develop branch, we typically merge in all the, we immediately merge in all the changes that people make. And then after some time, we'll have a release. And that means we merge in the develop branch to the master branch. and we give it a tag, which is essentially just a name, and in our case, it's just a version number. Next slide. So let me come to the development point. And as soon as you have cloned the code, or you downloaded the zip file, which I would not recommend, as I already told you, you have a couple of files and a couple of directories in this root directory. And I just want to briefly go through some of these directories and what files we actually have in there. And you can see that I grouped it here by the source code, by files that are used for running the code, files and directories used for testing, and files that are related to the build system. And these are not by no means all the files and directories, but these are the most important ones. So in SU2 CFD and in the common folder, we have the actual source code, C++ source code files. In the externals directory, we have also source code, but these are usually external packages that we don't usually touch when we add new features to the code. And this is why they are separated from the main repository, main source code files. The next one is the Python folder. So we have all the Python interfaces, all the Python scripts in there. Then we have the folders related to the running. So there's a small quick start test case that you can just immediately run because the mesh is already included there. Then there's a config template file, which includes, or should include, we should be a little bit better about that, but usually it includes all the available config options that you can put in the config file, along with a short description and the default values. Next one are the testing files. So we have unit tests, which I will talk about later, and also regression tests, which I will also cover later a little bit. Then we have the build system. So this is usually, these meson.build files are usually the files that you would edit if you would add new source code files that should be compiled along with the rest of the code. And the meson.py file is to run the build system file. So you have to run the meson.py file if you want to get started with compilation. Okay, then next slide. So if we look at one of these source code directories, for example, SU2 CFD or the common directory, you will see that there is an include and a source directory. Just a heads up here, that will be removed very soon because we opted already for having like the header files and the source code files in one and the same directory. So this is why it's here in brackets. So in the future, you will only see a source directory. And within that source directory, you have like different subfolders. And you already saw in the introduction talk from Tom that we split and moved a lot of files already because we want to have like more files, but they should be much smaller. So we organized all these files in a logical structure. Like you can see here for SU2 CFD, the drivers, the gradients, integration. In the common, we have basic types, geometry, linear algebra, and things like that, and even more. We are almost finished with that process, but not 100%. But that will be ready in the coming month, I guess. Next. Before you start coding, there are some topics that you should get familiar with in C++. First of all, there are some concepts that you should get familiar with in C++. For example, classes and polymorphism, virtual functions, pointers. MPI for parallelization would be good if you know about the basic concepts, but it's not really 100% required to implement things. And then, like since 1 year or so, we made C++ global 11 globally available in the code. So you might see a lot of things from that, like the auto keyword, range-based loops, lambda functions. And if you have no idea what I'm talking about, then yeah, just look for it somewhere in the internet, or we can offer also a course on that very soon. Next. So these concepts, for example, the virtual functions and the classes, this allows us to abstract a lot of things in the code and to encapsulate the data that is there, and that helps to localize changes, or that helps that you can make localized changes very easily. So usually classes, yeah, or different instances or objects share a lot of common routines. For example, here with the solver. So we have the base solver class, which and then we have some sub solver classes like the Euler solver, the ink Euler solver, the heat solver, and they represent essentially a structure to solve a particular PDE. But they all use or have a lot of functions in common, and in order to avoid duplication of the code, we put all these functions to the C solver class, and then the child classes just implement what is different, essentially. Yeah. So you should get familiar with that because we leverage that really a lot. Next slide. So let's have a look at the high class or the high level class structure that you may encounter if you dig into the code for the first time. The first thing that you might see is the single zone driver, and the single zone driver handles the preprocessing of all classes necessary to solve a problem. And it's also the place where you might find the time iteration loop. The next step is the C iteration class, which handles the pseudo time iteration loop for all of our PDE solvers. The next class that you might see there, or the next classes, are the C integration classes, and they deal with one pseudo time iteration, and they deal with the whole multigrid integration if it's available. They also, so as a next class, they also contain the C solvers, and they actually do all the heavy lifting. So they set up the residual vector for the finite volume discretization, and they solve the linear system if we have, for example, an implicit method. Then in the iteration class, we also have the C output class, which handles the writing of the history to the screen or file and handles all the solution output. So as an example, you can see here some of the classes that might be instantiated. For example, in this case, it would be an incompressible turbulent flow with radiation. And we have some terminology here. For example, the main solver, which is based on the solver option in the config file. Then the other solvers, like the turbulent solver or the radiation solver, they are called subsolvers. And then, as an extra tip, for most of the classes, there exist factory methods, if you have heard about that. Otherwise, look it up. And there you can easily see what classes are instantiated based on what config options are set. Okay, next slide. So in order to create or to start the development, go to GitHub and create a new branch. But then you might ask yourself, how can I make sure to not break the code if I do any changes? How can I coordinate my work with others? And where can I get help? Well, for the last two questions, there's an easy answer. You post an issue on GitHub. You join our Slack channel, which you can find. The link for that you can find on the main page next to the Facebook and LinkedIn links on the top right corner. Or you can participate in the weekly dev meeting. Information on that you find also in the Slack channel. Next slide. But there's a better way of coordinating your work and initiating some communication with other people. And this is by creating a pull request. A pull request is a request to the project to pull in your contribution, which can be done from an internal or an external internal branch or an external fork. And this makes sure that you don't break the code, you coordinate your work with others, and you can get help. Next. So once you click on that button, create pull request, you can see this interface. So you should make sure that you submit the pull request to the develop branch. Then you fill out the PR template questions. You choose a descriptive title. You choose a label so that your feature is later added to the release notes. And then you can choose whether your work is ready or if your work is not ready yet. And we strongly suggest to open a PR as early as possible, even if it cannot automatically merge like it's shown there, and even if it's not ready yet. Next. Yeah, so what are the benefits of opening a draft pull request? First of all, coordination. You let others know what you're working on. Then you get feedback and help from experienced developers, which can guide you during the development process. You have automated testing, so you instantly know if something is broken or the results have changed in the commit. And you also have a faster review process because people already are familiar with the changes that you made during the actual development. Next. Okay, so once you're ready with your, or not only if you're ready, but also during the development itself, you get usually some comments from others. But just as a reminder, don't see these review comments as a criticism of your work. It's to help you and us to maintain a great product. And I can only speak from my own experience that you really learn a lot in this process. Then, if two people from the community approve that pull request and all the checks pass, you're finally able to merge it in. Let me come to the testing now. So next slide. So we have like a extensive testing framework for you to use. And this makes sure that nothing is broken, that the code compiles on platforms. And the nice thing is that GitHub already offers like a framework that we can use. So we automatically do unit testing, and you see more about that in the next talk by Clark Pederson. We run regression tests that compare results against stored values. And then finally, we compile it on Linux, Mac, and Windows. Next. And this framework on GitHub is called GitHub Actions. And we have set it up in a way that on every push to a branch opened as a draft pull request, the code is built, the regression tests run, and the unit tests are executed. And if any of these steps fail, you receive an email. But don't worry, only you receive the email, and you're not spamming others with this information. Next slide. So if you want to add your own regression test to protect your features, then first you go to the serialregression.py or the parallelregression.py file and just use this, for example, this NACA 0012 example, and just fill in your values here. So if the computed values, which are usually residuals printed on the screen, do not match the values stored here in that file, then the case will fail, and yeah, you get a notification by email, like I said on the slide before. Next slide. So the second step of this process would be to add some files, for example, the config file for your test case. And here we have to distinguish between just the config file and the mesh. So larger files typically go to the test cases repository, and the config files, which change more frequently, can go to the main repository. Next. Once your contributions is merged, there will be a release, which means that the development is moved to master, a new tag is created, binaries are created, release notes are published, and the new version advertised. Everything happens automatically, so make sure that you choose a proper title and a label for your PR when you set it up. Then the next. So this is the tentative release schedule for this year. We are already at version 7.05. We have maintenance releases every month and minor releases every 6 months. But that vary. And major releases, yeah, that depends on how many features we have. Next slide. So this is just a quick recap of the things that I already told you and a best practice guide. I don't want to read that out for you. You can read it yourself when we put up the slides online. And then, yeah, next slide. And this is my final conclusion. So all of that was pretty easy, I guess. Don't worry, we have set up like a lot of safety nets. We removed the overhead wherever possible. Please try crazy ideas in your branches and don't be afraid of making big changes to the code. The community and infrastructure will be here to help you. And yeah, this is how we make progress. And with that, I conclude, and I hope to welcome you as an SU2 developer soon.
Great, thanks, Tim, for the great overview of development. So just a comment before we take a couple questions. We have some reports that the audio quality is a little bit hit or miss here on GoToWebinar. So I just want to remind folks that you can dial in by phone or also check the live stream on YouTube, where hopefully the audio might be a little bit better if you're still having trouble. So sorry about that. We're going to look into it and do our best. Tim, there are a couple questions. Maybe we just have a minute for one while we transition, but let me read one out loud for you. So somebody asks, is there any code standard format that should be followed?
The formatting for the code, you mean?
Yes, yeah, I think that's what they mean. The format.
Yeah, so we recently put like if people are familiar with CLang format, we recently put a format file in the source code directory. It's not yet automatically done, but we might think about that in the future. But you can use that file to format the code in the style or in the standard SU2 style, I would say.
Okay, and then there's only one more that we'll do real quick before we switch. Somebody is asking if there's a class with mathematical functions already built in, so matrix multiplications, vector multiplications, etc.
There are some small helper functions for that. There's a toolbox folder And there are some small functions for small matrices and small vectors available, yes.
Okay, great. So thanks again, Tim. Why don't we do the transition here? We're right on time. So thanks again for your great talk. Next, I want to introduce Clark Pederson, who's going to be speaking to us today about a very recent addition to the code that we're excited about, which is a unit testing framework inside of SU2. So he's going to discuss a little bit about the methodology and the philosophy. And so, Clark, if you're on, go ahead and take it away when you're ready.
All right, can you hear me?
Yes, sounds great. Go ahead.
Okay, so let me check and make sure I have control of the keyboard. And I'm not seeing my slides respond. There we go. All right. So I'll be talking a little bit about the unit testing framework in SU2. And so the first question that pops up is, why are we concerned about unit testing? We have some tests already in SU2. Why did we need a unit testing framework? And so that also comes up with other questions about what is a unit testing framework? How do unit tests and validation tests differ? And aren't validation tests sufficient? Aren't the tests we already had in SU2 sufficient? And then to also address the audience, this is for anyone from a person who's submitting their first changes to SU2 to the experienced developers. Unit tests can benefit you all. A lot of times, the first changes that people make in SU2 are on a unit level, a very small, tiny little bit of code. So this talk applies to those people doing small little changes to SU2 just as much as the people who are experienced developers. So a lot of my talk is going to be drawing from, and if you want to read more, you can go to these two books. The first one on the left is a staple. It's a book that every software engineer should have, working effectively with legacy code. And Michael Feather's talking about legacy code is in code you personally did not write and code that is not fully tested. And that matches SU2 for most people out there. And then modern C++ programming with test-driven development on the right focuses more specifically on unit tests and how you can apply them in C++. And these are both great texts. If you want to know more and dig a little more into the details, these two books are books that you should have. So the question comes up, why do we need unit tests? And this comes from working effectively with legacy code. It's a quote that says, code without tests is bad code. It doesn't matter how well written it is. It doesn't matter how pretty or object-oriented or well encapsulated it is. With tests, we can change the behavior of our code quickly and verifiably. Without them, we really don't know if our code is getting better or worse. And this quote seems a little powerful, but it also reminds me of my time I spent a summer working with some colleagues at NASA Langley. And in that experience, I talked with them a little bit about how they wrote code and what they did when they were writing code. And some of the people there I asked them, how often do you write unit tests? And they said, all the time. We don't make a single change to the code without writing unit tests to cover it. And that really shocked me, that someone doing scientific computing, where sometimes we neglect unit tests, are being very thorough and very rigorous about unit tests. And so I would like to move towards that with SU2. Obviously, SU2 is a community effort, and so it depends on you all as individuals. But I would like to move to a point where every single time we change a unit, we have some sort of test to verify that those changes worked. So the way programming oftentimes works is what we would call the edit and pray technique. And that is, we study the code, we make sure we understand the behavior, and then we make careful little changes. Then we pray that it'll all work, we run the validation tests, and we hope we didn't screw anything up too badly. So this, while it's the common way that we do scientific computing, there's a couple problems. Sorry, there's a little bit of lag when I'm changing slides. So one thing is that with a code base as huge as SU2, it would take a long time to fully understand it. And you may say, well, I don't need to fully understand it. But if you don't fully understand it, then there could be changes that you make that affect some part of the code you don't even know about. And that's not to scare you off. That's why we have unit tests. Unit tests help solve this problem. Another problem is that little unintentional mistakes can happen. I've seen more than once in SU2 code where somebody forgot a negative sign, and I've done that myself. Not all mistakes will immediately break the code. And then you also will spend a lot of time trying to understand the code. You'll make changes, but then future programmers will have to do rework to understand the code that you came to understand. That is obviously a waste of time. If you can somehow document what you expect the code to do, that'll be much more effective. So as an alternative to the edit and pray, there's another methodology you can have, and that is the cover and modify technique that Michael Feathers talks about in his book. And that's we cover the code with relevant tests, we ensure that the existing behavior isn't broken, and we ensure that the new behavior is correct. This is a little bit like when you paint something, you cover up everything that's not related so you can just paint that one thing that you're worried about. Then you don't have to worry about anything else. You're just worrying about this one thing that you're focusing on. Except here, instead of painting, we're actually testing.
Hey, Clark, this is Tom. Sorry to interrupt. If you're having trouble with the slides, go ahead and just tell Juan next, and he'll flip them for you. Okay.
All right. All right. So then the question comes up, so why do we need unit tests specifically? Why aren't the pre-existing tests sufficient? And so I can give three cases or three examples where a unit test is much better than a validation test. Obviously, there's room for both. I'm going to talk about that a little bit. Unit tests don't replace validation tests, but there are cases where unit tests are what you want instead of validation tests. And so one example is if you're developing a new feature and you want to test and see if the things you just coded work. Now you could do a full simulation, run it to convergence, but that would take a lot of time and a lot of computing power. If you messed up something like a negative sign, you want to know right away. You don't want to know an hour from now or a day from now. So unit tests let you run a quick test, verify that the changes you made work without throwing a ton of computing power at it. Next slide. Another example is if you submit a PR and then you discover that one of the regression tests failed. A lot of times it's not clear why the regression test failed. You know something broke, but you know something broke in the entire mess that is the giant code base. And so if you want some sort of more granular test coverage that shows that this one specific part of the code changed, then you can isolate that with a unit test, show that the previous code, this worked one way, the new code, it works a different way, and you can show that that's what broke. Next slide. And so the other example is if you're fixing a very small bug, a lot of times the code changes just something very simple, very small, very straightforward. And you want, obviously, then to have a simple, small, straightforward test. If we made an invalidation case for every single little bug fix in SU2, we would have hundreds of validation test cases. And that would just take forever to run. It would be unwieldy. So you want to have a small test to cover a very small bug fix. So those three examples are examples where unit tests really are better, and we should be focusing on those as well as validation tests. Next slide. A concern that oftentimes comes up is I don't have time to write tests. I don't have time to write unit tests. Isn't it sufficient that I just write the code, I make a validation test, and I show that it works? And then that brings me to a hypothetical question. If you just finished writing some code and you had to choose between finding a bug now and finding a bug in a year, which one would you choose? Obviously, if you can fix a bug in your code now, it's going to be so much easier than going back into the code a year later, trying to relearn what you did, and then having to fix it. So one study that was done at Microsoft found that test-driven development, writing unit tests as part of the development cycle, it did increase the development time by 30%, but it also decreased bugs by 21%. So that's the trade-off you have here. You spend a little more time in development, you have less bugs. So now that we've established when and where and why you need unit tests, I'm going to talk a little bit about how the tests in SU2 work, how it's implemented. Next slide. So first off, what do I mean when I talk about a unit testing framework? So on the left, you can see how you would do this with just raw C++ code without any sort of unit testing framework. And on the right, I have a unit testing framework. So on the left, we have some function adder, and this isn't even really necessary. It's just a simple example of a function. Yeah, so can I control the mouse? Okay, so yeah, I'll point at this stuff. So on the left, we have a function named adder. And obviously you don't need this if you're programming. It's just to show a simple example that's easy to understand of what a function might be. And so we want to check that the adder function works. So we add 2 plus 2, and we want it to equal 4. So if we run our test, that's the main function. We check that 2 plus 2 is equal to 4. If it's not equal to 4, we print an error, we exit with a failure, and we show what the results were. Now, this involves a lot of boilerplate code. So instead of that, we can reduce it down to something simple where we have the same function. We include the header file from our unit testing framework, and then we have a couple macros here. It's test case and require. And this checks everything for us. It checks that this is equal to this. And I'll explain a little bit more on future slides about that. The other advantage of a unit testing framework is it gives us a lot of powerful capabilities. For example, you can, instead of just running all the tests, you can filter tests so that only specific tests are run. You can exclude certain tests from the unit testing framework in its default run. There's a lot of much more powerful tools that come involved with the unit testing framework. So instead of having to do all the coding yourself every single time for every single test, a unit testing framework just gives you simple macros, simple tools to write quick, easy to understand tests. Next slide. So to go at a very high level over the overview of what's in SU2. So when implementing this unit testing framework, we decided on Catch2, which is a header file only unit testing framework. It's already in SU2. It's in the externals folder. That's on the most recent release and the development branch. So if you have the most recent release, you have this in there. All the tests are placed in a top level directory called unit tests. And then when you compile the code, a single test executable is compiled and run. So whenever you run Ninja test or Meson test as a command at the command line, only a single success or failure will be shown. That'll say the test driver as a whole failed or the test driver didn't. Then you can go into the logs or run the test driver itself in order to see which tests actually broke it during the testing process. Next slide. So here's an explanation of what everything is in a unit test. So the header up top here is what contains the macros and all the other things that we use for the unit tests. The test case macro just says this is a test case, and everything within the scope of the curly brackets is our test case. The addition is correct, string is the name. Now, unlike some of you may be experienced with other unit testing frameworks, one thing that I like about Catch is that the test names are actual strings. They don't have to be any sort of correct variable name. You just use a string and that's the test name. Same thing with tags. The tag right here, arithmetic, is the just a string that you put on, and you can have multiple tags. And the other advantage is multiple tests can have the same tag. So you can lump a group of tests together as all under the same tag. And then in here we have that if you add 2 plus 2, you should get 4. This is similar to an assert, if you're familiar with asserts in C or C++. It checks that the contained logical statement is true and it'll report an error if it does not. Next slide. So one important thing in scientific computing is we also have to talk about floating point arithmetic. That there can be errors at the level of machine precision, especially when you start stringing together a bunch of multiplies and divides. And these aren't necessarily an error in the code, it's just the machine can't calculate to infinite precision. So there's a helpful class, I believe you would call it, a helpful object that comes with Catch called approx. And you can wrap either the left-hand side or the right-hand side of any of these tests in this approx. And this just tells you that our pi has to be approximately this number. And you can even customize it with different levels of relative error with Cylon and different levels of absolute error with margin. So this is how you would test a floating point number so that you're not checking for absolute precision, you're checking for a machine level of precision. Next slide. All right, so I'm going to walk through a minimal working example. To keep things simple, I'm not actually going to pull up a terminal. I'm just going to walk you through these slides. And if you want to work through this tutorial on your own time, you can code it up yourself right now, or you can go back. These slides are going to be available online, and you can just walk through it yourself. So the first thing you would do is you would go to this unit test folder in the SU2 directory, and you would add your own file. Now there is a bit of structure in there, so when you go to add real unit tests, you want to add it in its own place in the folders, and it mimics the folder construction in SU2, so it shouldn't be too hard to figure out. But for a simple test case, you can just put it in that unit testing folder. And so here we have the same thing. We're adding two numbers, and we want to check that 2 + 2 is equal to 4. Go to the next slide. So then you have to make sure that this test actually gets built. So you would go in and you would go to the Meson, which is the build system. You would go to meson.build in the unit test folder, and then you'll see a little line that says add any new test files here, begin unit test listings, and then you want to add it to these lists right here. So I added here tutorial.cpp at the end of this list so that it will run our tutorial. Next slide. And then to compile it, you need to make sure you add this flag, d-enable test equals true, to build and compile the flag. So you would make your build directory, you would run the typical Meson command, and then you add this flag to the Meson configure command. And then when you go to build it, there's nothing else that you need to do. Next slide. So running tests, one way you can do it is you can just run Meson tests that'll build and run all the unit tests. And when you run Meson test, you would see something like this on the output. It would say, okay, I'm running the catch2 test driver. Everything exited okay. It exited successfully. And here's where your build log would be written to. If any tests fail, you can check that. Next slide. There's another way to run that, and if you're familiar with how Meson works, Meson wraps around Ninja for the build process. So you can invoke Ninja manually, and you get pretty much the same output, since Meson is just wrapping Ninja for the build process. Next slide. The third method is to actually run the test driver manually. That Ninja wraps around Meson, Meson wraps around Ninja, and Ninja runs your test driver. But you can also just run the test driver yourself. It's an executable. And so if everything's working, you'll see something like this. All tests passed, 12 assertions in 4 test cases. Next slide. So which method to use? The first two ones are simple. If you're already running Meson, if you're already running Ninja, you just add an extra command, Ninja test or Meson test, and you're done. The third method is important because it gives you the most control over the test driver. And I'll show you what I mean on the next couple of slides. So this is one example, is if you want to see the passing tests, you can add this -s for successful tests. And this is a part of the output. You would see that our unit test tutorial passed. We required that 2 + 2 is equal to 4, and that became 4 is equal to 4. So that test passed. And you can see much more detailed output of the successful tests. Next slide. So another option is to list tests, and this tells you all the tests that are available to run, both their names and the tags. And you can see here we have our addition is correct test that we added with an arithmetic tag. Next slide. Another thing you can add onto the test driver executable is if you add as an argument or a parameter to the test driver addition is correct, you'll see that it's only running the tests that match this test name. So it's only running our addition is correct test instead of the numerous test cases and numerous assertions we had before. We're just running one assertion and one test case. Next slide. You can do the same thing with tags. Only run tests with a specific tag. So here we're only running tests with arithmetic. And once again, we're only running our one assertion from our one test case. So even though by default, the test driver will run through every single unit test, if you want to just work on your unit test, you can use these filtering by test name or filtering by tags to just run a subset of the tests. Next slide. So to show you what would happen if you make a test fail, you can go back into this test and you can just make 2 + 2 = 3 and see what happens. And so can you go to the next slide? So if we recompile the test by running Ninja again, Ninja test in this case, we can see that now instead of the test being okay, the test is now failing. And next slide. If you actually run the test driver yourself or you look in the log, you'll see something like this, that the test failed. 2 + 2 is supposed to be equal to 3 according to the test, but we got 4 is equal to 3. And you can see that 4 test cases, only 3 passed, 1 failed, and out of all the assertions, in other words, all the required type statements, there were 12, 11 passed and 1 failed. Okay. So, and to just introduce a little more, in a short little presentation like this, I can't get into a lot of the details. There's a lot that's possible with Catch2. For example, you can group your tests into sections so that if you're repeating the same setup and teardown over and over, the tests can all share a setup and teardown. You can also have parameterized tests where you run the same test with a couple different parameters. You can log the context so that when failures are reported, you see what's going on in the code at the same time. You can have tests based around exceptions, that an exception is thrown due to something happening in the code and you check that that exception is thrown. You can also hide tests from the default list. That means that when the test driver is run, it doesn't run that test, but the test is still there if you ever want to run it manually. You can also launch GDB whenever a test fails, and that's done automatically if you do it correctly with Catch2. And you can also set up custom matchers if you know what that is. So for all of those, you can actually go to the official Catch2 documentation on GitHub to see how to do all of those. They have pretty good documentation and it's pretty straightforward. Next slide. So there's a lot more than just this talk about how to write and run unit tests, and that's on the GitHub SU2 documents that you can see here at these 2 websites. And then also I linked here the Catch2 GitHub repository where they have pretty extensive documentation about how to use the Catch2 testing framework. Okay, next slide. So just to finish up this talk, I want to end with another quote from Working Effectively with Legacy Code, and that's, remember, code is your house and you have to live in it. That I know I personally do not like unit tests. I don't know how everyone else is, but I don't like writing unit tests. It gives me a lot of comfort, it gives me a lot of security, but the actual act is not enjoyable. So I view it as like cleaning or as like doing any other household chore. That I do it so that at the end of the day, my house can be in good working order and I can be comfortable and secure in my house. It can be a bit of a chore sometimes, but the feeling you have at the end of the day is great. I love being able to write a bunch of unit tests, make a change, and then be able to go back and see that all my unit tests are still passing. That's a beautiful feeling to know that all my changes have not broken anything in the code, that the code is still working well, and it's as basically you can sleep safe at night is what some people say. And so remember, code is your house and you have to live in it. All right, and that's it. I can take any questions now.
Hey, great. Thanks so much for that, Clark. I couldn't agree with you more. I think, unfortunately, it was an oversight that we didn't have unit tests integrated at the beginning, but I'm very, very pleased that you've integrated it and connected it for everybody else. So there's plenty of time for questions. I'm looking through the question list now. So if you have any questions, I'll remind everyone, please just put them in the GoToWebinar question dialog, We'll read them out loud, and even if we don't have time to get to all of them, we'll forward them on to the speakers. So don't be shy in leaving the questions. We'll make sure they get answered. So please do drop any questions in. We'll speak to those. Okay, a couple are coming in. Let's see, I'll read them out loud. So someone asks, does your code need to pass other people's unit tests? Are they disabled in the master version to improve efficiency? I guess it's two questions.
Okay, so yeah, so to unpack those two questions, your code is expected to match other people's unit tests. And to back up a little bit, this is part of the philosophy of unit testing, is I can make a feature, I can cover it with a couple unit tests, and that describes the behavior that I expect to see out of that code. Then someone else can come in, write changes, and if those changes don't affect what I'm doing at all, they shouldn't break my unit tests if I've done my unit test correctly. If the two pieces of code we're editing don't interact at all, you won't have any problems. The unit tests won't interact with each other. However, if you start changing things that I coded, then that could make my unit tests fail. And that is a signal that whatever I thought was supposed to happen in the code is not happening anymore. Now that's okay if that's intentional, but it is a red flag if you code something and then suddenly you see that it broke something that someone else was assuming, someone else was expecting. It's a red flag that tells you to stop, make sure you understand what you're doing, and then figure out whether or not that test needs to be changed, or if that test, or if you need to fix something on your side. As another question is, to improve, are these tests enabled by default to improve efficiency, or are they disabled by default to improve efficiency? So these tests are run separately as part of a test driver. At this point, there's no changes on the SU2, you could say, side of SU2. The SU2 CFD, the SU2 Pi, the SU2 Geo, all these different executables. Nothing is changing with those. Those are compiled as libraries and linked into the testing framework. So when you're running your CFD simulation, there is zero overhead introduced by this unit testing framework. It's only when you use the unit testing framework that there's any overhead.
Okay, great. Maybe a general comment to add there. I think you mentioned this, but the unit tests are now also run automatically on GitHub. So anytime people put up pull requests, the unit tests are part of our testing suite. So you'll these will be checked if you make any changes. It'll be checked against these. So there are a couple more questions quickly. So someone asks, is this similar to assert?
Yes, it's very similar to assert. There's a couple different other checks you can make. And the advantage that this has over assert is that you can separate it off into a unit test so that it's not run every time the code is run, it's run in a separate unit test. And then it also will display information, as you saw when we had 2 + 2 = 3, it told us that we were trying to get 4 to equal to 3. Whereas if you're familiar with asserts, it doesn't really tell you much, it just tells you something failed.
Great. And there's one more question, and then we'll transition after this. Someone asks, what is the procedure to verify your results? And is there any comparison tool? I guess this goes a little bit in the direction of V&V, but so maybe out of the scope, but maybe you can comment, Cliff.
Yeah, I don't fully understand it. I'm going to guess that this question has to do with how do you verify that your code, and that goes back to what behavior are you trying to introduce. So an example I've done in the past is, I'll give an example. I noticed that I thought there was a bug in how the viscous residuals were calculated for the energy equation. And so I stepped back and then I looked at it and I set up tests to show that in this test case, I expect the residual to be this. And I checked that. In another test case, I compared the ideal gas residual with the non-ideal gas with an ideal gas inserted as the quote non-ideal gas, and checked and made sure that I got the same two results. And when I saw that both tests failed, I knew I had found a bug. And then I stepped back and I fixed it, and then that all worked. And then so I went from 2 tests that failed to 2 tests that worked. So it's a very general question. There's no one size fits all answer for what should your unit test look like. It's just a question if you have to ask yourself, what do I expect the code to do? And then you test that it's actually doing what you expect it to do. That it's calculating the right residuals, it's calculating the right derivatives, it's calculating the right interpolation, those sorts of things.
Great, thanks, Clark. Thanks again for the great talk. And I really encourage all the developers to begin incorporating the unit test framework into their process. So this is something we hope to use more and more as we go. So now I want to switch speakers. I'd like to introduce Toby Kattmann from Bosch, who is going to be talking about an area of the code that's seeing a lot of development lately, which is how to set up multi-zone problems. So Toby, whenever you're ready, if you want to turn on your camera and take it away.
All right. Thank you, Tom. I hope you're able to hear me loud and clear.
Audio is good. Yep.
Okay, perfect. So hello, everyone, and welcome to this presentation on how to set up multi-zone problems in SU2. I included today's date and the current master's version number because, as Tom mentioned, things can move quite quickly in SU2, so that you just all know what this presentation refers to. Oh, just one slide too quickly. Yeah, I will talk about 3 major points, which are firstly mesh handling, what is a zone, and how do you set up a mesh, and how do you get it to work with SU2. Then in the second step, how to set up config files appropriately for that a multi-zone simulation can run. And at this stage, I already want to mention that we will have one master config file and one zonal config file for each zone. That is important for some things already in the mesh. And the third point deals with everything around output. And amongst other things, I will introduce the ParaView multi-block output format, which I personally really like and is, I think, also interesting for single zone users. Before we jump in, a few disclaimers ahead. This, of course, is by no means my work. I'm just presenting the current state to our best knowledge. And instead of listing a lot of names, I just thank the SU2 community as a whole. And the second point, during the preparation for the talk, I briefly looked into things like fluid computations and other stuff, which I usually do not use. And I noticed some slight inconsistencies here and there, and at moments where I thought, well, that's a bit counterintuitive. And chances are that you found at least one bug if you work with SU2 long enough. And that's why I want to stress here that SU2 is developed by many PhD students, postdocs, and other people from various organizations over the time without having a common boss or process that decides what has to be done. So things like these can happen. And I think the SU2 Foundation is doing a great job to keep things together here. And also because of the things I just mentioned, yeah, I cannot cover all topics and I do not cover edge cases. And sometimes I just leave out certain parts to cover the most basic things. This tutorial is, of course, for everyone who wants to set up multi-zone computation and has a bit of background in SU2. But I think just having run the quick start tutorial, taking a look at the config files and the mesh should be enough of preparation. And this presentation is, is more of a tutorial character with practical aspects and is not a full theory guide. and it's certified 100% equation free for that reason. So with that out of the way, let's jump into the mesh handling. So first off, what is a zone? On the left side, we have an image here for CHD computation with 3 solid domains and 1 fluid domain, and these domains are separated through interfaces. And in this CHT case, it's pretty straightforward. What is a zone? So it is a multi-physics case. So in the zones where are different physics, that is a zone in SU2. So heat conduction and fluid flow in this case. For an FSI case, we would have, for example, a wing, which would be the structural domain, and the flow domain. So we would have 2 zones there. That would be a zone. And also important, the different zones do not have to be connected necessarily. So we have the middle pin and the outer pin, but they can be included into one zone. That is important for the mesh later. And another case would be, for example, a fluid-fluid case. So in this example, we have a channel with a pitching airfoil in the middle. And we could simulate that having a rigid mesh for the channel and a rigid mesh for this circle with the airfoil in it. And we could use these 2 rigid meshes and just impose a grid movement on the inner mesh. So we would have a fluid-fluid simulation here, and that would also account for a zone for that middle mesh. And also in these cases where we have not multi-physics, but we have, in case fluid-fluid, we can also talk about multi-zone single physics instead of multi-physics. Then that's something you can set up a bit differently later in the process for the config files. But I will talk about that later. Now that we have defined what is a zone, we can take care about the meshing. And just as I said before, for the 2 images on the left, you can see you can have 4 zones for that example. So you have each solid zone independently, or you just add these zones together if you solve the same physics here. So heat conduction in the red zone, and in the black zone, you would have Navier-Stokes equation, for example. For the interface boundary markers, you have to take care that these are geometrical pairs. That is, that they cover the same area or the same line. You cannot have, for example, in the fluid, in the upper image, 1 marker for all the pin surfaces, and each zone has a separate pin surface. That wouldn't work. So you have to make sure that the interface markers are matching. One comment also towards MPI, each rank gets a chunk of each zone. That is, in that lower example, if you have 2 ranks, the fluid zone and the mesh decomposition would be separated in two domains, and the solid zone as well. So that is important, for example, for multi-grid methods where total number of elements per core is somewhat important. And as a side note also, the mesh is written independently and is used internally independently. And it's also for internal structures like config files and solvers. They are kind of independent in the code, and there's only a communication via the common interfaces of the multiple zones. Now, how can you incorporate your mesh or your multi-zone mesh into SU2? There are 2 main possibilities. The one is with the config option, multi-zone mesh equals to no, where you would specify the single zone mesh in each config file. So just as in single zone computations, you create a mesh for each zone, and in each zonal config file, you specify your zonal mesh. Or you can create a multi-zone mesh with that option. And the creation of that multi-zone mesh, which is then just one file, is pretty straightforward. You need to use the keywords nZone to specify the total number of zones, and then iZone followed by the mesh just copied into the file. That's everything you have to do. So just put nZone, iZone, copy the mesh into, repeat that for the different zones, and you're good to go. And then you just have one mesh which you can use later. And the order of the meshes in this mesh file is important in the sense that it is used later also in the order of the config files and so on. So I already mentioned we have multiple config files. So we have a master and we have zonal config files. And of course, that puts up the question of hierarchy, what happens when options are set in the master and in the zonal, and what actions have to be in the master, what has to be in the zonal config file. So let's unfold that and take a look. So the master config file is shown here. Above, there's the default value. And in the lower bracket, we have the zonal config files. Okay, and let's start with the master. All options that you set in the master are also used for the zonal configs. So they internally, they are copied to that config instance. But if that option is also written in the zonal config file, the zonal config overrides that option. So the zonal config kind of has the last word. If an option is neither set in the zonal config and the master config, the default value is used. So that is kind of the hierarchy of config options. And on the next slide, we will take care about what options have to be used in the master and in the zonal. But one suggestion from my side ahead, I think it is reasonable to first try all single zone simulations independent. So you take a config file, you take your mesh, and you just try to get it to run. Therefore, of course, you need to have your interfaces applied with some arbitrary marker that kind of makes sense. Then you create a master and add every option that you need for multi-zone computation and try to keep it as slim as possible. And then you can go on and transfer common options to the master because of that hierarchy that sometimes makes a lot of sense. For example, if you have one fluid zone and 5 solid zones, it could make sense to have common options from the 5 solid zones put into the master, because then you just have one place to change that option. Otherwise, you would have to change it in each zonal when you want to change it. So you can use that config file hierarchy to your well-being. And in the, for example, then in the fluid config, you could set that option as well, and that would override the master. So you would have less options overall that you have to set. So how to set up the config files then? So you have to specify solver equals to multiphysics in the master config file. There you can go with a different approach for the fluid cases, as I said earlier. There's a different way to do it, but I found that this approach works also for fluid cases, so we'll just go on with that. Then you have to decide about how you want to incorporate the mesh. So do you want to use the multi-zone mesh format, or do you want to use the single mesh format? And then, of course, that means that the mesh file name goes either in the master or in the zonal configs. Then you have to specify a config list where you just add all the config files which you want to use separated by a comma. And here you just have to also follow the order that you prescribed in your mesh. So the first mesh gets first config file and so on. In the next step, you have to add the zone interface markers into the master config file. And these have to be pairs. So for example, you have one marker in zone A, and it gets its kind of its brother wall B or sister. And then you go on and add all the interface marker pairs into that list. And the last thing you have to do is you have to add some information about how many iterations you want to do. And I will cover that point later a bit more in detail. For the zonal configs, you just have to make sure that you delete all the options which interfere with those. So for example, I said already for meshes that you'd have to delete the mesh file name if you use the multi-zone mesh. And also do not use the interface markers again in the zonal file names because you already set that in the master. You start your simulation just with invoking SU2 CFD on the master config file, just as in the single zone, but now you just have to call the master. Okay, now for a little example. So let's assume we have on the left our zone A config file, and on the right our zone B config file. In this case, I just use a conjugate heat transfer simulation with the heat equation and in compressor Navier-Stokes in the fluid. And now we set up our multi-zone config file. So the first thing, as I said, we have to set solver equal to multiphysics in our master config file. In our zone config files, we leave the option for the solver as is. The next option is the mesh. So in this case, I decided to use the multi-zone mesh. So I set that option. I include the mesh file name, and I delete the mesh file name from the zonal configs because we do not need that anymore. Okay, now I just add the list with the config files, and I forgot the comma here in the list. But something else which is notable here is that \character. So that's actually something new in SU2, that you can use the \character in a list to concatenate multiple lines. So before, if you have a long list with markers or anything else, it would have to be in one line, and that line could get very long. Now you can use that \character to actually use the next line and to make the config file a bit more readable. I think that's really nice to use, especially for multi-zone files. Now we add the marker zone interface, and notice that in the zonal configs, I used like some marker whatever here. So in the Navier-Stokes, that could have been marker heat flux, and in zone B, that could have been marker isothermal, for example, where I just use that to check whether the single zone computation is all right. Now I just write them as pairs into the marker zone interface, and here we just have one common interface, so it's just one pair. In case of a CHT simulation, we also have to set marker CHT interface and use the same markers here. For others, for other physics, or for example for FSI or for fluid cases, I advise you to either look into the tutorials or into the test cases to see how that is handled specifically there. And we also then going to delete the marker for the interface from the zonal config files. Okay, now we move on to iter, or to the iteration specification. And this is something we will cover a bit more detailed. So for single zone steady, we only use the config variable iter. Then, if we have single zone unsteady cases, we use time iter, and for each physical time step, we do inner iter pseudo time steps. So now we use inner iter here for this kind of iteration. If we move now to multi-physics simulation, we need to incorporate the communication via the interfaces, so the coupling. So we need to include a new kind of iteration, which is called outer iter here. So the hierarchy here is we have time iter, outer iter, and each zone gets an inner iter. And for each outer iter, we do the interface coupling. If we apply that to our little test case, we could start with having inner iter for each zone equal to 1, and just putting what we had for iter before in outer iter. So in that case, that would mean that we do 100 iterations of our simulation, and in each zone we would do one pseudo time step and then do the coupling via the interface. In other simulations like FSI, but also in CHD, it could make sense to use multiple inner iterations, but that's something that you have to take away a bit from the test cases, the tutorials, and maybe try out for yourself. The last bits here in the zonal configs, which we have to take care about, is stuff related to output. So a screen output, history output, and output files. And we already see, we can already see a problem. So if we want to, for example, unify that here into the master config somehow, because especially for screen output, that would make sense to just have it unified on the screen. How is evaluated in the master, whether, for example, drag refers to the zone A or to the zone B. That's really simple. We just add the zone number in square brackets behind the name. And that, of course, only applies to options that are zone specific. Something like outer iter, that is the same for both zones, so that does not get here in the zone ID. You can always look for your simulation what is valid output by using the dry run mode, using SU2 CFD -D, and then invoke the config file. So in that case, you would use SU2 CFD -D master config, and you would see the valid outputs for screen, history, and volume output. The last point here is the output files, and you already see that I moved it from the zonal configs into the master. That also means that restart and paraview multi-block is written. And this paraview multi-block is something that I want to take a closer look to, because I think it is really nice also for single zone users. So if you use the paraview multi-block format, it will write a VTM file, which is basically an XML style file, which links into such a folder which is created where data for each zone, each boundary, and the internal is written. So here we would have the name of every boundary marker and something called internal. And that is all written automatically. Before in SU2, we had the concept of having like a separate volume and surface output, and that kind of unifies it and makes it very easy to use. You can, of course, still always write output for each zone independently and load that into your post-processor of choice, like paraview, tagplot, visit, and so on. This multi-block format, of course, is only available for paraview in the moment, and I do not know if any other post-processor can actually load that. So, and I also want to show you a bit how that paraview multi-block format actually looks like. And I have a little GIF on the next slide that will show it a bit better. But few things ahead. Now every boundary and every internal is its own block, so you can work with it. You can select and deselect them as you like. You can apply filter. You can extract blocks, and you can just work with it. So let's start the GIF. I hope it is fluent for all of you. And I just open paraview by calling the master, the config master.vtm. And first I will make the lines a bit thicker so that you can see everything nicely. So that's the image we just saw before with the VTK block colors. And now I go to View, Multi-Block Inspector, and that will open, or that will add a new tab where I can select and deselect the internal. For example, here I deselect the fluid inner, and I can also select all boundary conditions, which also allows me, for example, to deselect everything but the inlet and the outlet and compute something like pressure drop very, very easily. Of course, I can do it by a screen output as well, but it's also possible to do it like that. This is the extract block filter, which is really nice to, as the name suggests, extract certain areas of the mesh and do, for example, you can visualize some boundaries in another way than the internal. So you can do things like that. And that's it for that little GIF. I really hope that more people use ParaView multi-block, because I think it's a huge step forward for compared to how it was before. A few words towards the discrete adjoint capabilities concerning multi-zone. So gradients by discrete adjoint via the discrete adjoint methods are available just like in single zone simulations. You have to take care though about the formulation of the objective function. You have to set it in every zonal config explicitly, because if you do not set anything, you will get drag with objective weight 1 evaluated on the marker monitoring. That also happened to me. So make sure that you, for example, set the objective weight to 0 in a zone where you don't want to have a contribution from. It has to be said though that some Python script, or I think all Python script, are not compatible yet with the multi-zone adjoints. So for example, shape optimization will not work out of the box right now. And this feature, so the multi-zone discrete adjoints, were implemented by Ole Burkhardt from the TU Kaiserslautern. And I also included an image with heat flux sensitivities for both zones for heat flux on the inner pin. And if you are interested in that, you can go to that little tutorial he wrote on the GitHub page. So check that out if you want to learn more about that. Okay, so that's it for the talk. I hope I covered the basic things about mesh creation, multi-zone config files, and a bit of output considerations, so that now you can just go ahead and set up your own multi-zone computation, which should be really easy, right? Yeah, as I mentioned before, for FSI, things are a bit different for fluid cases, and there are a lot of things to consider. So if things do not go according to plan, oh, I didn't want to end the slideshow. So if there are some problems, you can first check the website. You can go through the test cases. I think that's a really great possibility. Or if you really encounter a bug or something that doesn't work, you can go to CFD Online or write a bug report on the Issues tab in GitHub and include me via my handle. And I hope you learned something today, and thanks for tuning in. And yeah, I hope I can answer some questions now.
Great, thank you, Toby. And yes, you do have some questions. So we have maybe just a minute for one or two. So there are one or two that I think would be very useful to share out loud. One is a question as to whether the interfaces need to be geometrically matched. So are they point to point, nearest neighbor, conformal, non-conformal? So can you say a word about that?
Yeah, I forgot to mention that. As was shown on the mesh, it's actually possible to have non-matching mesh. So there are different types of how you can add the interpolation. So you can have nearest neighbor versions, which also works with non-matching mesh. but there you would probably use something like radial basis functions. So the mesh does not need to be matching. And actually, even if it is matching, if you set it up matching, it only uses nearest neighbor method. So it does not expect you to have matching mesh. Just like shown here with on the upper image, you see that zone 2 and zone 0 are connected via non-matching mesh. So that's totally possible.
Great. And there's a related question asking what kind of interpolations are available and whether it's conservative in the data transfer.
Okay, that's I know that we have nearest neighbor and radial basis function, but I'm not too much into that. So I know that there's also different methods like weighted average, which is I think mostly used for fluid. Yeah, I don't know too much about the internals, I have to admit.
I can say we had a paper a couple years ago related to the FSI work where we were doing consistent and conservative interpolations. So those kind of routines are available. I can point you to that paper. The person who's asking the question, we can take that offline. And then maybe there's one more question. So somebody asks, does the ParaView multi-block output feature work for single zone simulations as well?
Yeah, and I highly recommend to use that. That's it. Because you will have all the features as I described, you will have it. So you will have the same folder, but just with one zone. You will have all the interface, the boundary markers. I think it is, it's better usable than like the surface output and volume output separated like it was before. So if you just take one zone away, it works the same way.
Okay. And maybe one last one. I think we have break next, so we'll spill over just a moment because I think this could also be useful for folks. Is it possible to track the characteristics at the interfaces between zones during the iterations?
Oh, that's something I have to admit I do not know.
So if Tim's online, maybe he could say a word if his audio is still okay, because I believe we can customize this output. Yeah, Tim, you want to go ahead?
Yes, that should be possible, but I think it is limited at the moment to certain predefined things. But we're working on customizing that even more so that you can define some custom functions on the interface.
Yeah, great. If you take a look in some of the output classes, there are places where you can define new values on surfaces and whatnot. So that one might take a little work, but know that that's under development. We're working on it. Okay, we're a little bit over. We're supposed to go into break now. So why don't we go ahead and stop here and pause and come back right at 8:40 a.m. Pacific. So that's 7 minutes. And we'll pick up the next set of talks at that point. So thanks again, Toby. And we'll be back in about 7 minutes, everyone. Thanks.
Okay, great. Just next slides, please.
Oh, Rahul,
Next slides.
we're
Yeah.
just waiting until 8:40. We won't begin just yet, but I thought you
Okay,
wanted
sure.
to test that.
Yeah, just can I look at the next slides a little bit? That's all. Yeah, now it's okay. Okay, thanks. You can go back to first. Yeah, it's fine. Yeah, thanks. Mhm.
Okay, welcome back from break, everyone, at 8:40. So now we're going to jump into the second half of our program for today, which contains a bunch of great lightning talks. And I'd like to introduce the first speaker, who is Rahul, who will be talking to us today about a modal analysis platform in SU2 for computational aeroelasticity and applications in linear and nonlinear reduced order modeling. So Rahul, when you're ready, take it away. And if you can, turn on your camera, please. Thanks.
Yeah, okay, great. Hello everyone, I'm Rahul. So today I'll be talking about a modal analysis platform in SU2 for computational aeroelasticity and applications in linear and nonlinear reduced order model. And this is part of my PhD work that I finished a couple of months back, and I have been supervised by Dr. Murali Damodaran and Professor PC Khu. Currently, I'm working in Temasek Lab, National University of Singapore, as a research scientist. Okay, next slide, please. Next slide, please. No, please. Yeah. So let's look at the presentation outline. So first, I'll talk about the development of a platform for modal analysis of aerodynamic surfaces like wing. Then I'll talk about how to compute the generalized aerodynamic forces in the SU2 environment. Second, I'll talk about the code implementation details in SU2. And then finally, I'll talk about the applications in linear and nonlinear reduced order model. Next slide, please. Yeah, so before looking into the problem formulations, I will first talk about the aeroelastic equations, typical form of aeroelastic equation immersed in aerodynamic flows, which is mq double dot plus cq plus kq. There's, I think, one q dot is missing, equal to the aerodynamic forces, where mass mc and k is basically mass matrix, damping matrix, and stiffness matrix. So if you do the eigenvalue decomposition, you will get eigenvalues, which is lambda I, and the eigenmodes, which is phi I. So these eigenmodes are the structural modes, like first bending, first torsion, second bending, second torsion. And if you project the governing equation over the structural modes, so you will get the structural equation in a generalized coordinates, which is eta double dot plus natural frequency squared into eta equal to fz. This is the z directional force times phi transpose. So as you can see that fz and q, these are having the dimensions in the order of the structural mesh, but once you project it over a reduced space, its order is the same as your structural modes are. Like if you have taken 4 modes, your phi t fz will have 4 degrees of freedom, means you will have 4 generalized aerodynamic forces. So now let's look at my problem definitions, like what exactly reduced order model, how have I implemented reduced order model in SU2 framework. So what I have to do, I have to excite the aerodynamic surfaces like wing with a in the modal directions, which is eta, under a white Gaussian noise signals, like as you can see. And then I have to compute the generalized aerodynamic force, which is phi t fz from the SU2, which is coming from high fidelity NS equations. And then finally, I have to build a linear and nonlinear reduced order model, which is non-intrusive in my case. And once the ROM is generated, now I can give any other input excitation, be it sinusoidal or structural input. I should get back the corresponding GF. So that's the whole story. First, excite the random noise, generate a reduced order model, and then excite it with a sinusoidal signals, and you can get back the GF what you want. Okay. So next is this is my volume mesh that I have done it in pointwise, and this is the mesh near the wing structure, and this is the wing surface mesh which is structured in nature, and this is the structured mesh that I have used in the NASTAN for the FE analysis. Next slide. Yeah, as you can see that a FEA mesh in the Nastran should exactly match the span of the fluid mesh here, which is developed in the pointwise for the fluid solver. Next slide. Okay, so now the fluid and structure should talk to each other. Like if I give a structural excitation to the structural mode, and then a fluid mesh must have to excite in the same way, and I have to compute the forces first, which you can do very easily in the SU2. Like as you can compute the FZ forces in the SU2 very easily, but the problem is that I have to compute the GF, means I have to multiply it with the phi, that is the structural modes. So we'll see that how to compute those things inside the SU2 environment. Next slide, please. Yeah, so this is the typical framework. So first you have to compute the structural modes in the Nastran. As you can see, this is the first, fourth, second, and fourth, first, second, third, and fourth structural modes computed from the Nastran. Now, what I have to do for development of the ROM is that I have to excite the fluid mesh, wing surface in the fluid solver in the same modal directions that like this structure modes are showing, and I have to give any kind of Gaussian signal for the development of the ROM, or it could be simple harmonic signals, as well as sometimes you have to keep impulse signals, whilst step inputs, anything is required, but you have to give in the modal directions. But in SU2 it's little difficult to give this kind of arbitrary deformations. Like usually you can give rigid pitching motion, rigid plunging, or any kind of 6DF motions, but it's little difficult to give this kind of arbitrary motion in the plunge in the modal directions, which is of important in my case. So one possible way is to couple it with the FFD box that is already inside the SU2, but I have done it in a different way. So first I have computed the modes in the Nastran solver, and then I have used MATLAB for a polynomial interpolations. I have used fifth order or third order polynomial, anything is fine. Third order doesn't work well that much for the fourth mode, but you can use radial basis function as well. And then you have to convey this message, convey these coefficients to the SU2 solver, which deals with the grid movement solver, and as well as the solver which actually deals with the force coefficients. So two important CPP file I have, C++ file I have actually modified. One is grid movement structure.cpp and solver direct mean.cpp. So grid movement structure.cpp resides inside the SU2 CFD SRC, and it resides in the common SRC, and solver direct mean.cpp resides in the SU2 CFD SRC folder. So I will tell in detail how to modify those things. And then finally, once the Gaussian excitation is given in the first modal directions, I should be able to produce linear and nonlinear reduced order model. Next slide, please. Okay, so now let's look at in particular how to implement it in SU2 in particular. So like first, my objective is to give it a random excitation in the modal directions, that is phi1 directions, and I have to give it to phi2 direction, phi3 and phi4, and accordingly I have to compute the generalized aerodynamic force as well. So for that I have modified, I have not built any other functions inside the C++ environment in SU2. So I have modified the existing solver, which is inside the common SRC folder. There is a grid movement structure.cpp, and I have modified this function C surface movement surface pitching functions. So which is basically connected with the deforming mesh, since I am giving an arbitrary motions to the wing surface. So definitely your mesh movement is not going to be rigid motions. So deforming mesh is way more suitable here, because there is another folder, another function called rigid pitching. I cannot change that because that is associated with the rigid mesh motion. So I thought this would be more suitable. So what I did here, I just computed the MATLAB coefficients and conveyed that message to the surface pitching solver. Like as you can see that the coefficients, MATLAB coefficients are conveyed here. And now initially inside the normal SU2 environment, you could have give normal pitching motion or plunging or any 6DF motion. Now it will only listen to the MATLAB coefficient that you have delivered here, and it will exactly move in the directions that you want to for your modal excitations. And as you can see, I have given sinusoidal excitations in that mode 1 directions. Like you can see, 100 is the frequency radian per second, and it is giving, you can give here any kind of Gaussian signals, step function, anything. So if you want to give a discrete values as well, that also you can do. You have to write another SU2 double variables, and you have to write in a matrix form what are the discrete values you want to add here. Okay, next please. Yeah, so next page, next another objective here. Now I have to compute the GAF. So in SU2 you can easily compute the z directional force, which is lift force basically. Now what I have to do here, now I have to couple it with the modes. So that modes I have represented here in that MATLAB coefficients in a polynomial form. So as you can see, that SU2 double basis is the new variables I have introduced for representing the modes. And then force 2 is the basically lift force that is already computed inside the SU2. Once I multiplied them, I get the phi 1 times fz, so which is basically the first GAF. Means you have excited in the first modal direction and you have got the first GAF. So that is very important to develop the ROM or any ROM applications or any other aeroelastic application of interest. Next slide, please. Okay, so now that's the application in linear reduced order model. So it is very much for different aeroelastic instabilities, one of them is flutter phenomena, which associates very small deflections, and linear reduced order model is sufficient to represent the flutter cases. So that's why I have used linear reduced order model, which is non-intrusive in nature, and it's a subspace identification based method. The ethics, the philosophy is same. You have to excite them with a random structural motions, and you have to get the aerodynamic forces, and you have to compute the machinery that will talk to the structural input and aerodynamic output. So once that reduced order model or machinery is done, you can give it any input, whether it is sinusoidal, cosinusoidal, whatever, or if you couple it with structure, it will give you a complete aeroelastic solver as well. So here in the applications, actually as an example, I have shown both the training and test signal as same, which is the random Gaussian signal, and it has matched quite well. But you can give any kind of signals like sinusoidal, even the structural input can be coupled to. So this more of the methods can be find out in my recent paper, which has published in AI journal, but it's mostly focused on the 2D. It has not any 3D results, but the detail of the methods will be more clear if you look at the paper. Next slide, please. Okay. So now, if your aircraft wing associates large deflections, even at high Mach number where flow separations as well as the shock motion becomes extreme, the input-output relationship does not remain linear in nature. So you need to have a nonlinear functional relationship between input and output. So that it's just an extension of my previous work, and between the structural input, which is given again in that SU2 in the modal directions, and the corresponding GF, I have formed an LSTM based deep learning based model, and there are the different hyperparameters associated here. I won't go in much detail. Here again, I have given both the training and test signals as same, but you can give any other signals and it works perfectly well. And as you can see,
sorry to interrupt, just a time check, about 1 minute, okay?
Okay, sure. And this work has been published in the AI journal, but it's not online yet. Next slide, please. So now this is the GitHub repository. I have given all my codes and as ROM codes here. Yeah, you can have a look and give me feedback. Yeah, thanks. Any question?
Okay, great. Thanks, Rahul, for the nice talk. We are a little tight on time. There's maybe one question I'll ask while we start the transition. So someone asked, can you repeat how you're doing the interpolation of the modal shape from the structural grid to the fluid domain boundary?
Okay, so here actually in this reduced order model, my structure and the fluid are completely decoupled. Means I can solve the structure completely separate from the fluid itself, just because structure is linear in nature. So now what I compute the structural modes in the NAST run, and then I compute the modes, and then the modes I need to interpolate using MATLAB interpolation function, which is polynomial in nature. So once I know the polynomial coefficients, I just give that polynomial coefficient to the surface pitching that grid movement structure.cpp solver inside the SU2, which earlier actually give me the pitching motions. So now I am telling, don't go in the pitch directions, go in that MATLAB coefficient direction. I am giving you the I am directing you. So that is how actually I have modified. Yeah, but I have not yet developed the user ends. That would be another good contribution here. Yeah, that's all. If it is clear.
Okay, great. Thank you, Rahul. And there might be one or two more questions that we'll pass your way. So we can take those offline. Okay, I'll forward them along.
Sure. Thanks.
Okay, so thanks again. And now we'll transition to Arturo, who is going to join us from USC to talk about extra scalar transport equations inside of SU2. So you should be unmuted, Arturo. So please, if you can hear us, take it away.
Yeah, hello. Can you hear me now?
Yeah, sounds great. And if you have trouble with slides, just tell us and we'll flip them, okay? Just say next.
All right, I think I'll just rely on you. Thank you. So hello everyone, and thank you for joining to this this presentation on extra scalar transport equations capability in SU2. My name is Arturo Cajal. I am a PhD student in the Aerodynamic Design and Research Laboratory, Professor Uranga's research group at USC. So before starting, let me first share you the motivation and approach to do this work. So next slide, please. So what we have here is the generic scalar transport equation, and with appropriate boundary condition, it helps us to predict the behavior of scalar quantities such as mass or temperature in a physical system, which of course is relevant to many engineering applications. One example of these equations are the RANS models to simulate turbulent flow. And SU2 has demonstrated its credibility for RANS solver in the verification and validation process, where solutions showed really good agreement with both experiments and other well-known CFD packages. So one approach for further improving the accuracy of these kind of simulations, particularly for low Reynolds number and transitional flows, is to include additional scalar transport equations to model the transitional behavior. SU2 does not currently have this capability, so my goal is to do this, implement a transitional model to be solved alongside the main flow and the turbulence solver, and thus expand the framework to accept an extra scalar transport equation or equations depending on the model. So unfortunately, these haven't been accomplished yet. Although its implementation is in the last stages, I am getting a divergence problem after the first iteration of an steady state problem. So I will talk about the implementation, but unfortunately not the results. So this might be a talk a little bit different to the others. And also part of this goal is to get some feedback about how the implementation should be. But for now, let me move on to the code development. So current transition prediction capability in SU2 is limited to two models, the VC model, which the transition onset parameter is determined based on experimental correlations, which of course limits its range of applicability to that for which the model was calibrated for. And they also have the Lang-to-Mentor model, which is partially coded but not functional yet. And I will also like to point out that this model relies on empirical correlations. So talking about the model, next slide, please, that I decide to implement, let me first introduce Humberto Medina's laminar kinetic energy model. And the main idea behind this model is that there exist some pre-transitional velocity fluctuations that appear as 2D traveling waves carrying most of its energy in the streamwise component of the velocity. And these fluctuations travel and evolve in space and time, extracting energy from the main flow until an eventual breakdown to a turbulent state. This is supposed to be a standalone model. However, the version that I'm presenting here is coupled with the standard K omega turbulence model by Wilcox. And the turbulent eddy viscosity is computed by adding the effects of the small scale fluctuations, which is coming from the turbulence model solution, and the large scale fluctuations, which is, in the case of natural transition, we can think of those as TA's waves, or in the case of bypass transition, as oscillating outer flow. The values of the constants and some other functions are more detailed in Medina's paper. So to begin with the models implementation, next slide, please. And following SU2's physical modeling procedure, we need to first define the convective and viscous fluxes, as well as the source terms for the equation. So I'm doing that for the three equations that I showed: the turbulent kinetic energy, the specific disintegration omega, and the laminar kinetic energy Kl. So next slide, please. If you're a developer in USC, you might be familiarized on the process on how to treat a new PDE in SU2. So the first thing we need to do is to build a new solver class in where the state vector is defined and also some allocation is performed, as well as the loops that control the computation of each term and the boundary conditions are defined. Then a corresponding variable class that contains the state vector at each mesh node, and as well as some auxiliary data is created, and finally the numerics class. So these are kind of the three main classes that we need to implement or to create. But there's some other changes that we also need to include. So starting with the solver, I would like to highlight some of the functions of the solver. So the constructor by itself, where we define the state vector dimension. So for the case of the turbulent solver, this would be n variable equal to, so two equations to be solved. And obviously for the case of the transitional solver, it would be just one. Then we define and allocate some vectors, such as geometrical vectors or the primitive variables flow vector, and some other structures such as the Jacobian. So as of now, I would like to point out that all the implementation that I'm doing right now, it's for a single grid. So yeah, also within the constructor, we initialize the solution to the far field state everywhere, and we perform some allocation of the inlets. Then also within the solver, other methods that need to be defined is the loops for computing each term. So the upward and viscous residual methods are just inherited from the turbulent solver, and the source residual depends on the model. Next, please. So other two functions to highlight is the pre-processing and post-processing. In the pre-processing, we just initialize the vector and the allocated vector and the Jacobian matrices. And then in the post-processing, here's a summarized version on how I'm computing and setting the eddy viscosity. I say it's summarized because I'm not fully showing how I'm computing FSS, for instance, or how I'm getting the density rho from the main flow solver container. But thanks. But anyway, this is how it's implemented right now. So for each point in the mesh, we go and get the solution from the turbulent solver, so K and omega. Then we get the laminar eddy viscosity from the solver container. And then we compute the eddy viscosity. These functions are given in Medina's paper. And finally, we compute the eddy viscosity. And as I showed before, this is done by addition of the small scale and the large scale fluctuations. At this point, I would like to highlight that I have this mu t. I set this max value to avoid negative eddy viscosity, which is a non-physical value. And finally, I use this set mod function, the mu t function, to put the eddy viscosity everywhere in the mesh. Next slide, please. Then also within the solver, the boundary conditions are defined. So for the test case that I'm implementing right now, which is a zero pressure gradient flat plate, the relevant boundary conditions are just the Euler and symmetry boundary conditions, which are inherited from the turbulent solver. But we just know that the fluxes across these boundaries is zero. Then the non-slip condition that within SU2 is just a heat flux wall with a zero flux of heat. Then a far field, and an inlet and outlet boundary conditions. The far field is not used in this scheme, but it's going to be used when we try to do the test case for variable pressure gradient flat plates. Next slide, please. So now moving on to the variable class, here's where I said that we store the solution and some other coupling variables, but as well we also store some auxiliary functions such as the transition initiation function that triggers the transition in the laminar kinetic energy model. Next. Also, the numerics class is defined here. So the convective fluxes and viscous fluxes are just inhering methods from the scalar methods already embedded in SU2. So the convective flux is just computed using an upwind scheme, and the viscous flux is computed using the cell average gradient method. And as I mentioned before, the source term just integrates the source at each mesh node. Next. So other things to keep in mind, as I said, the solver, the variable, and the numerics classes are the most relevant. But also in the pre-processing, we just need to make sure that we're having all the options ready and properly set to run the simulation. So basically, the input and output processing is how we're going to communicate with the config file and how we're going to be communicating with the console afterwards. Define the containers for the solver, numerics, integration, and iteration processes. And once that we're doing, and as I said before, I'm just implementing this for a single zone iteration method. We just need to make sure that in the function of the fluid iteration container, we include the options to solve the transition model using a single zone iteration method. So this iteration happens once that the solver begins. Next slide, please. So as I said before, implementing a new equation in SU2 framework seems to be trivial, but there are some challenges to it. So right now I'm getting this numerical divergence problem in which my turbulent kinetic energy from the turbulence model is going negative, which is a non-physical value. So I'm in that process right now. I'm doing the debugging. I'm exploring the idea of setting a max or min, similarly to what I did with the eddy viscosity. Not sure if this is going to be needed for all the iterations or just for a couple of them to make the solver stable numerically. Right now, I'm having this inability to visualize local residuals in the domain to perform some debugging. So at each time step, I can print the root mean square of these residuals. However, I cannot visualize them locally in the domain. So I guess that would help that would be helpful in the debugging process. And these two last bullet points, as an engineer by training and not a computer scientist, it was just challenging. This is not a critique to the code, completely the opposite. I really love SU2, the framework, how it is thought to be solved any kind of PDE. However, this was just challenging, and along those lines, like making sure that we're coupling the transitional solver properly within a runs framework with the main flow and the turbulence solver. So with all this said, next slide, please. I would like to really happy to answer any of your questions, and thank you.
Okay, thanks so much, Arturo. I think it's a very nice presentation. Debugging is part of life, so there's no need to feel bad about it. And in fact, I like that you're bringing up all your development issues so we can have some discussion, maybe connect some people. So there's time for a couple questions. I'm seeing a kind of a consistent thread in a couple of them. Folks are asking how this work compares to some of the other work we've seen that also has extra scalar equations, and maybe I can add personally to this, what's your plan for integrating this? And I think you've seen that we have an open pull request on GitHub, et cetera. So maybe you can just make some comments.
Yeah, so I've been working with Tobias Kattmann a little bit on his request, on his PR of the scalar transport equation. So we can just think of this as a specific case of implementation of a scalar transport equation, and the future work would be use this as base classes to expand the framework, and then just have all the infrastructure to add an arbitrary number of scalar equations. So basically, the answer would be this is just in a specific case. I'm just making sure that it runs, and once that it runs, since many of the methods for computing the viscous and convective fluxes are shared, maybe perform some abstraction and then construct a framework to treat all the scalar transport equations the same way.
Yeah, great. So I think it should be pretty natural that all of these talks or all the work that you see that includes scalars, they're going to leverage the same underlying classes. So I think
so that's kind of the main idea, constructing the framework to accept all these equations, sharing all these methods for computing viscous and convective fluxes and source terms. So yeah.
Okay, there's another question here about your choice of the convective scheme for the scalar transport equation. So why you're using scalar upwinding, and why you haven't considered using something like what else is available there. So there's Rho, HLLC, and AUSM. But I think that the key point here is that for an additional scalar equation, what we have available is scalar upwinding. So I don't know if you have any comment.
Yeah, I mean, I'm just using this because it's the one that is implemented so far with the turbulent solver, and within the framework of RANS, I just want to be using the same thing. But definitely, we can repurpose many of the methods already embedded in SU2 to compute the convective fluxes. So as I mentioned before, this is just can be thought as a specific case, but the main idea is to expand it afterwards to accept any kind of these equations.
Arturo, this is Juan. I had a question because you had a comment regarding the ability to visualize residuals and various other things as the code runs. Have you considered the possibility of looking at pair views, in situ visualization and just sort of doing a quick coupling with SU2? I don't think anybody in the community has done that yet, but then you'll be able to visualize anything and everything as the code runs.
Yeah, I mean, that sounds like a good idea to be implemented. I didn't think about it yet, but yeah, that could be.
Maybe we should add that to the discussion tomorrow that we will have on future developments, because I think that there'll be interest from others.
Yeah, definitely. I agree.
Yeah, that would be great. I think it is probably possible to add the residuals for your equations to the output with just a little bit of work. So we could also discuss that too. Maybe we can take that offline and help you out with that. So that's something we could do if we could probably talk about that over GitHub or over Slack.
Sounds great. Yeah.
Okay, great. Well, thanks again, Arturo. We should probably switch here to the next presenter. So thanks again for your talk.
Thank you.
At this point, I'd like to introduce the next speaker, Christophe, who will be talking to us today about a compact scheme for real gas flow simulation. So I can hear you well, so go ahead and take it away, Christophe.
Perfect. Thanks very much. So this work has been performed at École Centrale de Lyon by Michele Romanelli, who's a master student, and myself. So I'm going to, if I can, yes, fine. Oops, sorry. I'm going to start with a few words on what motivates this implementation of the so-called RBC scheme in SU2. I will then proceed to briefly describe the key design principle of the scheme and make a short comparison with a row scheme. Then say a few words on the real gas extension, which was no big deal. And I will conclude with a few words on the future work. So if you want to perform, say, some steady compressible simulation with SU2, probably you will set up with a second order calculation. You will choose some second order upwind scheme, for instance, row scheme with reconstruction to ensure space accuracy, and then you will select implicit to achieve fast convergence to steady state. And basically, what will happen is that you will have a second order upwind scheme with some extended stencil because of the reconstruction, coupled with an implicit stage, which will be basically first order, so on a more compact stencil. And of course, this is a good point that you have a compact stencil first order type for implicit stage, because it's a reduced cost per iteration. But it's well known from Fourier analysis that this lack of stencil consistency between explicit and implicit stage translate into some reduced efficiency of the implicit treatment. Of course, in SU2, you also have, for instance, agglomeration multigrid, which is available for convergence acceleration. Still, it can be really interesting to try to implement a second order scheme, which is expressed on a reduced stencil closer to the one used by the implicit scheme, so that you can achieve a better intrinsic efficiency. And this should be provided by RBC. So a few words on RBC. They were initially actually developed on Cartesian grids, okay, and they are kept being developed up to a large order, okay, for unsteady calculation as well. And to keep things simple, on a Cartesian grid, you can achieve with this scheme second, actually even third order accuracy in 3D, a 3 by 3 by 3 stencil. If you want to do the same thing with a conventional, say, row scheme or approximate Riemann solver with reconstruction, we all know that you would need 5 + 5 + 5 points per direction. It has been extended to unstructured grids, but only in a cell-centered finite volume formulation. So the present work was to actually implement in SU2 RBC in this vertex-centered framework. So a few words on the design principle to understand how it was implemented. You start with the first order raw numerical flux. So we all know it. You have this centered part, and then you have this matrix dissipation you add, which is based on the absolute value of the eigenvalues of the Jacobian associated with the normal flux to the face. If you want to go second order with this strategy, you know that you keep the same flux, but then you replace the states at vertices by reconstructed states at the face, and then you need, of course, a gradient, and with the gradient, you go to an extended support. With RBC, you have the same, basically the same form, okay, of numerical flux. So you have this centered part for the convective flux and the dissipation, which is also a matrix dissipation. But the key point is that it no longer uses this difference of states. It uses the residual, and the residual vanishing at steady state to build the dissipation. So the point is you need to, so you're going to build this dissipative flux as follows. It's going to look quite similar to the one that you can write for the row scheme. Difference is here you have your dissipation matrix, but it's a bit more complex, okay? It relies not only on the, say, the normal eigenvalues, okay, associated once again with the Jacobian computed from the flux normal to the face, but it also makes use of the, let's say, transverse eigenvalues. I'm not going to detail this. This is well established, and you can extend it without any issue. And the point is, up to now, we've been using states I and j on each side of the edge. And so now we need to build and to compute this residual. And to do this, we're going to compute this on a shifted cell, okay, well chosen. And this I'm going to describe on the next slide. Okay, so you need to compute your residual instead of your state difference. And here I reported the, say, the dual cell around state and vertex I. And so for each face of this cell, I'm going to compute my numerical flux, and the dissipative part of this numerical flux, it will make use of a residual, which will be computed by computing this contour integral of the convective flux. So what you need, okay, will be the convective flux at the point here, for instance, I and j, plus, of course, the convective flux estimated at the center of the cells here. But this, you can have a sufficiently accurate estimate using only values at the black dots here, which means that eventually you achieve second order dissipation on a stencil, which is actually the one that you would be using for a first order row scheme, for instance, or first order approximate Riemann solver. So this is why we call it residual-based and compact. So we have implemented the scheme in SU2 for the time being only in 2D. Okay, so you can already guess what will be the future work. So it's proposed as an alternative to the raw flux. And the one other key point is we made nothing specific for the implicit treatment. So we directly reused the available implicit treatment. I'm just going to show one result. Okay, we have made, of course, several over calculation. I'm just going to show one which exemplifies what we can achieve. So it's a subsonic flow. We computed transonic, supersonic. Here it's simply subsonic, Mach 0.5, 2 degrees over the well-known NACA 12, and we are making use of one of the triangular grid available in SU2 test case database. So here I report the convergence to steady state of row scheme, first order in orange, row scheme second order in green, and RBC in red. And for each scheme, it's too small, okay. But we've been using actually the maximum CFL number, offering the best convergence we could achieve. On the left, I'm showing the density residual, and on the right, I'm showing the convergence of the lift coefficient. And so the good news is that even though there are still things to fix, of course, for instance, regarding the behavior here, but the nice point is you can achieve actually what you expected from the start. You can achieve a faster convergence to steady state because you have a better intrinsic efficiency for the same accuracy. Actually, you have the same level of accuracy. From here, it's reported in terms of iteration. Okay, so of course, in terms of CPU, there are still optimization to perform clearly, because per iteration, the cost is roughly 50% larger. Okay, so next. Sorry, I think I can't. Okay, fine. I'm just trying to move to the next slide. Here it is. Okay, so after this test, of course, over one in 2D again, okay, only in 2D, but for different flow regimes, we move to real gas. So real gas, I put it in parentheses because actually it's no big deal, and it's no big deal because of all the nice work which was done before in SU2, of course. Otherwise, it would have been a big deal. So formally, the numerical flux is unchanged. You just need to deal with a generalized Jacobian. You have now you need to take into account the partial derivatives of the pressure with respect to density and internal energy, and these formulas, they depend on the equation of state you're using, be it in current SU2 van der Waals or Peng-Robinson. We implemented Martineau as well. And another ingredient which is available is the row average, the special kind of row average that you need to apply. And we're using with RBC the same row average that people use with row. So all this, as mentioned, is already available thanks to the good work of Vitale and co-workers in 2015. So we just make use of this. We put it into the RBC numerical flux, and I'm just going to show a transonic application with PP10 and using again the same first order, the same implicit stage available in SU2 for row and RBC. On the next slide, if I manage to move it, yeah, I'm just quickly showing the pressure contour, pressure coefficient contour. On the left, you've got two solutions, second order RBC and row, and they are actually very similar, and you can further analyze this. On the right, it's just to show for those not familiar with real gas, the perfect gas calculation with RBC for the same condition, okay, but perfect gas. So accuracy is fine, and regarding efficiency, again, I'm showing on the next slide convergence to a steady state obtained using the maximum allowable CFL numbers, so respectively 5 for RBC, 2 for row. And again, we were quite pleased. I'm not showing the first order result here because I lost it actually, and but we were pleased with the improved efficiency of by RBC, keeping in mind we still have an over cost per iteration. Okay, so where do we go from here? What's next? We have some straightforward developments to perform, obviously. So 3D extension, clearly, okay, we've written things and we are currently coding it. We have some optimization we'd like to do on the boundary condition because of the way we use a shifted cell at the wall. What will be more involved will be the viscous extension. And since I'm running out of time, if people have questions, I will be pleased to explain what's the issue with the viscous extension. And just to conclude on a good note, we've actually implemented the version RBC still in 2D and still in VSID, but in the incompressible solver. And on the last slide, I just have a result showing a comparison for a flow of water. It was very straightforward because the incompressible flow solver is hyperbolic. Okay, so it relies on hyperbolic assumptions, so we could achieve the same accuracy as second order row with RBC. And this concludes my presentation. Thank you very much.
Thank you, Christophe. Wonderful results. So thanks for sharing that. We have time maybe for just a question or two if people want to add something. You have one very positive comment. So Alberto says, very nice presentation. Thanks.
Thank you.
And if anyone else has a question, we can take it. Here's so it sounds like somebody does want to know what the challenge is for the viscous implementation. Maybe we'll just comment, if you can comment on that, and then we'll transition.
Yeah, that's fine. Actually, I was precisely trying to move back to the previous slide. It should come soon with the lag. So it's no big deal. But the key point, what's very specific to this residual-based scheme, is that you're going to extend to the viscous case, you're going to have this centered approximation of the convective flux plus the dissipation, and you will have a centered approximation of the viscous flux. So this is as usual. What will be specific is that you won't have something decoupled between inviscid and viscous for the dissipation. Because since the dissipation is based on the residual, if you want to achieve true second order, you will need to include in the residual not only the convective flux, but the viscous flux. And this is what's specific. So it can be done. It has been done. We have cell-centered finite volume formulation of RBC for turbulent flows. Okay, but it's just that very often in solvers, you have this decoupling between the convective discretization and the diffusive discretization. And here you need to take part of the diffusive information, the viscous flux balance, to put it into the dissipation for your convective flux. That was the trick.
Okay, very good. Okay, thank you again, Christophe, for a great talk.
Thanks
and if anything comes up, of course, we'll forward you more questions if they pop up.
It will be a pleasure. Thanks a lot.
Okay, and now I'd like to transition to our next speaker. So Jessie is joining us from Stanford, and she's going to be talking about implementing projection-based reduced order modeling in SU2. So go ahead and take it away, Jessie.
Hi, as Tom said, my name is Jessie. I'm a PhD student at Stanford working with Professor Alonso in the Aerospace Design Lab. I'll be talking about implementing projection-based reduced order modeling in SU2. First, I'll briefly go over the concept of projection-based reduced order modeling and why it's useful. Then I'll talk about the implementation with SU2 and ideas for improvement. I'll go through a simple example with SU2 to demonstrate the reduced order modeling capabilities. And then at the end, I'll talk about plans for the future. In general, there is a need for surrogate models that are fast and still accurate. For example, in shape optimization, a surrogate model can greatly reduce the computational cost of the optimization loop while still retaining a high level of accuracy. For uncertainty quantification analysis, a surrogate model would be similarly useful. And in flow control, they may be useful to facilitate controller design or in a real-time feedback loop. For all of these examples, the surrogate model is used to predict the flow solution without having to start a full CFD simulation. For the shape optimization example, the authors used a PUD plus interpolation model. In uncertainty quantification, a statistical model is typically used. And the authors in the flow control example use machine learning plus Koopman theory. These are very brief descriptions of the models used, but shows that there are many options for surrogate models and also many uses. A projection-based reduced order model is a specific kind of surrogate model. The fundamental concept is that the full solution, say a 3D flow solution, belongs to a reduced subspace. By that, I mean if a CFD solution has 1 million degrees of freedom, the reduced subspace may only have 1,000. We'll call the matrix that spans this reduced subspace phi, and finding phi is the first step in creating a PROM. To start, several full CFD simulations are required. The solutions for these simulations are used as training data. Each simulation may be similar, but with a different Mach number, shape parameter, or any other parameter that you might be using. because the idea is to compute the full CFD solutions for only a few of these parameters, like Mach numbers, and then use a surrogate model to fill in the gaps. We then use this data to find phi, the reduced subspace. The algorithm for doing so is called proper orthogonal decomposition, which I don't go into detail here. Second, the governing equations like Euler or Navier-Stokes equations are projected onto this reduced subspace that we just found. In this space, they can be solved for a lot faster. The PROM framework then allows us to project or lift this reduced solution back up to obtain a predicted solution. The key takeaway here is that the PROM solves the projected equations in a much smaller subspace, which allows for the computational speedup. There are some details for the PROM that make this framework more difficult for nonlinear equations. After considering that CFD equations are nonlinear and they are also solved by minimizing the residual, the specific approach used for reduced order models for CFD is called the least squares Petrov-Galerkin projection. It is a Gauss-Newton iterative approach for reducing the residual or minimizing the residual. If you're familiar with Galerkin projection, a key difference is that the Jacobian is required for the projection step. And not only do we need to query the full Jacobian, we also need to multiply it with another large matrix. This makes this approach intrusive and expensive. The intrusive part is a more minor obstacle because SU2 is open source. However, we don't want the ROM to be expensive because that defeats the purpose of a surrogate model. To combat this additional computational expense, another approximation is introduced called hyperreduction. At every iteration, the predicted solution, residual, and Jacobian are only computed at a small subset of nodes and are ignored at all other nodes. To choose which nodes we keep, a greedy selection algorithm was implemented. The figure here shows which nodes were selected for an airfoil problem. It might be a little hard to see, but the yellow nodes were the selected nodes, purple are ignored nodes, and the bluish green color are the neighboring nodes to the selected nodes, which I also have to keep track of. The overall implementation is to apply a mask over the nodes and edges within SU2, which allows the smaller residuals and Jacobians to be calculated and used in the ROM iteration. Given that intrusive ROMs can be calculated to implement and create, what if anyone could create their own ROM? The capability of experimenting with PROMs could be in the hands of many more people. This is the goal of the PROM project in SU2. The implementation of the ROM in SU2 is straightforward. The idea is that a ROM could be created just from the options in the config file. For example, I currently have the ROM equations triggered if the math problem is ROM. Right now, the ROM specific code is mostly located in C solver and C Euler solver. In C solver, there are the pre-processing and offline computation routines, like the selection of the nodes for hyperreduction. In C Euler solver is the bulk of the code, including the main ROM or LSPG iteration. There are also alterations to the residual computation loops to accommodate for a hyperreduction. I think it might make more organizational sense for the ROM code to be in a separate C-ROM solver class. There would still be some if statements in C solver and C Euler solver, so it wouldn't be fully independent, but that's one idea. I also saw a PR about modules, which seemed relevant, so I'm keeping an eye out on that. And I'm also looking into ways to better alter the residual computation loops. These are just some things that I'm thinking about in optimizing the code that's already there. As a proof of concept, I created an example using the NACA 0012 mesh in the quick start tutorial for SU2. The simulation uses the Euler equations at Mach 0.4 and an angle of attack of 1.25 degrees. I ran 30 different simulations, and this is how I gathered the training data. Each simulation differs by shape parameter. There are 6 Higgs-Henny bumps, 3 on the top surface and 3 on the bottom surface, as noted in the figure. Higgs-Henny bumps are smooth bumps that allow for change in the design of the airfoil, and a setup like this might be useful for shape optimization. So this resulted in 30 different simulations for each of the 30 different airfoil designs. I then tested the ROM on an airfoil design that was not included in the training data. The figures here show the results of a ROM prediction that used 200 nodes for hyperreduction, or 3.8% of the total number of nodes. You can see that the error is less than 1% for the entire domain. The table below shows the speed up. The full Euler simulation without any reduced order modeling took about 49 seconds. This is wall clock time. The resulting ROM predictions showed a speed up of 10 to 20 times. As a proof of concept, these are good results, as this shows that a hyper-reduced PROM can work within SU2. We can also expect a greater speed up with a larger problem. Literature shows closer to 1,000 times speed up for a RAND simulation. In summary, I showed the capability of a ROM within SU2 and the goals of its implementation. In the future, I'd like to extend the implementation to include Navier-Stokes or RAND simulations. I'd also like to compare with other interpolation-based reduced order models. And I want to place the final touches on making this capability user-friendly, which also includes documentation. And the next major step for this work will be to look at space-time ROMs for unsteady applications. In this case, a space-time ROM will also reduce in the time domain instead of only spatially. Okay, are there any questions? I see I do have one question here.
Yeah, thanks, Jessie. Go ahead, and if you want to take it right off the screen, go for it. Maybe read it
Sure.
out loud as well.
Yeah, so the question asks which CPP files with the Jacobian computation and which one deals with the particular mesh points selection. Have you computed the modes, I think nodes offline, or have you coupled linear algebra package in SU2? So there's a couple of questions in there. The CPP files that deal with the Jacobian computation, and I'm working with the updated version of SU2. So the CPP files for the Jacobian computation are in the C Euler solver.cpp file. There are some in the, when I extend to Navier-Stokes, I will need to alter that CPP file as well. All of the Jacobian computations, or most of the bulk of that is in the residual computation loop. So that's where I'm altering the residual and Jacobian computation. And which file deals with the particular mesh point selection. So those functions are in C solver.cpp. All of my functions are at the very bottom of the file. There's like 4 or 5 that help me with that greedy selection algorithm to determine which nodes the hyperreduction will choose. And then I have coupled a linear algebra package. I use LPAC for the ROM iteration. There's a QR decomposition in there.
Okay, great. There are a couple more, maybe just one more I'll read for you, and then we can transition. So somebody has asked, have you tested the ROM at a transonic Mach number?
Yes, so I have tested it at a Mach 0.8 test case with the same mesh. It is a little bit harder, so I haven't gone back to that problem in a while. But if you have a shock in the solution, it's a little bit harder for the ROM to handle that because effectively the resulting ROM prediction is a linear combination of the POD modes. I can talk more to that. I didn't go over the POD as much, so if that's confusing, I can go into more detail offline. But the ROM does typically have, it struggles more with shocks, but there's still ways to handle it. It just, it's a harder problem.
Yeah, thank you, Jessie. So there are a few more questions. I'll go ahead and forward those to you, and you can just at your leisure respond either through the chat or as a follow-up later. So I'll pass those along. So thank you again for your talk. And we will, at this point, transition to the next speaker. So Mert is here coming to join us, and we'll be talking about adjoint-based multipoint airfoil shape optimization for a new generation of advanced trainer aircraft. So if you can hear us, the stage is yours.
Yeah, thank you. Hello, you are all welcome. Before I start, let me introduce myself. My name is Mert. I'm a master's student at Gazi University, and Professor Atilla Bikoğlu is my advisor. And today I will talk about adjoint-based multipoint airfoil shape optimization for a new generation advanced trainer aircraft. First of all, let me outline the presentation. First, I will talk about airfoils of trainer aircrafts. Then I will move to motivation, methodology, selection of the optimization points, objective and constraint functions, and I will show you the results and I will conclude the presentation. Here you can see some trainer aircrafts. These are Kai, KT-1T, Tucano, and these two are from Pilatus, PC-7 and PC-21. These three are the old aircrafts, and they have NACA 6 series airfoils. NACA 6 series are designed to get maximum profit from laminar flow. Because of that, these airfoils have a really minimum drag coefficient at subsonic region. But like PC-21, new generation aircrafts have their own airfoils to improve their performance. The motivation of the study is how much effective is the gradient-based optimization on multipoints with more than one constraint. One is that. And the other one, how much effective is the gradient-based multipoint optimization from a good baseline airfoil. In the literature, most of the optimization studies are have the baseline airfoil like NACA 4-digit series, and this study will show that the result. How much useful is the gradient-based multipoint optimization for industrial projects? And NACA 64-415 is selected as the baseline airfoil, and O-grid is generated with Y+1. Reference length of the airfoil is 1 meter. Far field distance from the origin is 15 chord length. Spallard-Almaraz turbulence model is used. Let me talk about these digits a little bit. 15 is the thickness to chord ratio of the airfoil, and this 4 is the design lift coefficient of the airfoil. 0.4 represents the design lift coefficient of this airfoil. This 2 is the range of the lift coefficient. It means that 0.2 and 0.6 lift coefficient between these lift coefficients, this airfoil have direct polar. And 4 represents the minimum pressure point, and 6 represents the 6 series of NACA. And in this line charts, you can see the grid independence. This shows us the drag coefficient change with respect to number of cells, and it shows that about 30,000 grid cells, the grid is independent from the number of cells. And 32 core computer is used in this study, and with respect to that, 1.15 growth rate is selected. As the optimization methodology, SU2 optimization loop is used exactly the same, just multipoints are included. Sequential least squares quadratic programming optimization algorithm is used, and you can see the Higgs and bound function effect on the airfoil. I choose two optimization points for this study. One is high speed condition and the other is maneuvering condition. High speed condition is defined as a top value of the trainer's aircraft's maximum level speed, and the maneuver condition is defined as an estimated low G maneuver of the trainer aircrafts. Weighting factors of the optimization points are equal. You can change that, and maneuvering condition is just as an estimated value. And these are the baseline airfoil results at these conditions. And now I will talk about the objective and constraint functions. Objective function is minimizing the drag coefficient at constant lift coefficient, and constraint functions are moment coefficients, thickness to chord ratio, and airfoil area. I would like to increase the constraint function. Constraint function boundaries are defined as estimated values from baseline airfoil. Now you can see the optimization phase results. At the bottom, black points are represents the NACA baseline airfoil, and red points are represents the optimized airfoil. And here is the results. As I said before, lift coefficient is keeps constant, and optimized profile has the same lift coefficient at lower angle of attacks. This means that at the 3D configuration phase, this might be an advantage for the fuselage configuration. And when we look at the drag coefficient, at the high speed condition, there is no improvement on drag coefficient. It's the same, 93 drag counts. And in maneuvering condition, 3 drag counts improvement is seen on the optimized profile. When we look at the moment coefficients, a little bit increase is observed at moment coefficient. When we look at the alpha sweep results at 0.5 Mach, and maximum lift coefficient, optimized profile's maximum lift coefficient is higher than the NACA baseline airfoil, and CL is maximum L over D is increased again, and moment curve slopes are similar between those two aircrafts, but optimized airfoil has a little bit higher CM0. When we look at the 0.35 Mach, again optimized profile has a higher CL max value, and in this time optimized profile has a higher stall angle, and the after lift coefficient is 1, optimized profile has higher lift to drag ratio, and again moment curve are similar between these two airfoils. And again, CM0 is higher for the optimized profile. Here you can see an animation of those airfoils. Actually, this looks like very similar. Here you can see the pressure coefficient distribution along the chord line. And actually, optimized profile has now irregularities up to half of the chord. There are some differences between them, actually, especially for the leading edge region. Optimized airfoil has a peak there at high speed condition. Now I would like to conclude the presentation. Adjoint-based multipoint airfoil optimization is performed with SU2. Optimized airfoils advantages are higher CL max, higher stall angle at 0.35 Mach, higher L over D max, and higher L over D at CL greater than 0.95. There's a disadvantage for the optimized airfoil is higher ZM0 value, but this is not completely an disadvantage because the when we think about the full aircraft, the downwash affects the tail also. And when we look at the numbers, stall angle is 1 degree is more higher. What about next? Optimization procedure will be performed with FFD box instead of XM bump functions. 2D flap and aileron optimization studies may be performed, including control surface deflection and hinge moments. Then multipoint 3D wing optimization will be performed. Here is my reference list, and if you have any questions, I can answer.
Okay, great. Thank you, Mert, for the talk. I think we have plenty of time for questions. So I actually have a first one for you, while other people should please put them in the question window. But my question for you, it's in your future work. You mentioned switching to FFD boxes. I was going to make a comment that sometimes it's hard to know where to place the Hicks-Henny bumps. It's a little bit difficult a priori to kind of choose where to put the control points. So I wanted to know if you've given that any thought of how you're going to set up the box, how many control points to use, etc.
Actually, I don't have any idea in this procedure, but I have to set up because the next procedure represents the 3D wing optimization. For the 3D, I have to use the FFD box.
Yeah. I would recommend when you switch over to the box, then also do some investigation into how many control points you put, how many degrees along each direction, and just play around a little bit to discover how many control points you need in order to capture what you're looking for. So I wish we had a more adaptive way to do it right now, but we do not. So
okay, thank you.
Yeah, and then if there are more questions, we still have time. So feel free to just drop them in the window in the question box.
Tom, in the meanwhile, I had a question. Mert, I was wondering if, since the airfoil design improved the performance so much, but you had some issues with slightly more negative CM, did you try to constrain the CM of the airfoil to the value of the original airfoil in order to see if you still had as large an improvement than the other measures of performance?
Actually, no, because the moment is not very important for the, instead of we would like to improve the L over D first, then the moment will be the backstage. I mean,
So it's
why
a secondary
is
importance.
Yes. Why is the moment coefficient is important? It's because of the trim condition, like, or something else. But it's in backstage.
Okay, sounds good. Thank you.
And maybe a final question. Someone's curious, if they don't have much exposure to adjoint methods, are there any general material or references? Maybe Mert, you could share if you have any papers you like to read, or maybe if you've published anything on this work, if you could share.
Okay. Actually, Tim's study is very useful for the adjoint method.
Did you say Tim's paper? So Tim Albring's paper?
Yes, that paper.
Yeah, I would say that's a great reference if anyone's looking to understand what's going on in the discrete adjoint inside of SU2. Tim's paper in AIAA, I think 2016, Tim, you can correct me if I'm wrong. I think we link it on the front page of the website. It has a very nice overview of the entire discrete adjoint implementation. So I highly encourage folks give that a look. Okay, at this point we should transition. So Mert, thanks again for your nice talk.
You're welcome.
And yeah, thank you. And at this point, I would like to turn the stage over to Charanya, who's joining us from Imperial. It's very nice to have you. And she's going to be talking about her work on discrete adjoints for unsteady fluid structure interaction problems. So the stage is yours, Charanya.
Thanks for the introduction, Tom. Hi, everyone. My talk today is about the development of discrete adjoint sensitivities for FSI problems, focusing on unsteady simulations with a view to use these gradients towards optimization. The work is done together with my PhD supervisor, Professor Rafael Palacios at Imperial College London. I'll structure the talk, starting with the motivation for pursuing this field of research and what we're trying to achieve. Then we'll move on to the technical background. Firstly, the direct solver to run unsteady fluid structure interaction problems. I'll then give an overview of the formulation for dynamic FSI discrete adjoint equations and the differences in implementation compared to static problems. Based on these, I'll present two test case results. First, for a fluid-only problem, but with enforced motion, which acts as a stepping stone towards FSI. And then I'll share the preliminary results so far on a dynamic FSI problem before concluding with a summary and an insight into the planned future work. Starting on motivation, why do we need to consider dynamic FSI for optimization and design? As the general trend in aviation is towards lightweight structures for fuel efficiency, either in conventional aircraft or in solar aircraft, these next generation aircraft introduce increased flexibility in the structure, necessitating the fluid structure interaction analysis. Steady state analysis helps to inform the baseline aerodynamic features and is typically used in optimization around design conditions, but the response to dynamic events often helps to size the structure. And therefore, we need to include this as well for comprehensive design work. The time domain analysis captures inherent instabilities as well as responses to external inputs so that we can simulate and perform optimization for problems with flutter, limit cycle oscillations, gust loads, etc. The optimization framework for static FSI currently starts with a baseline undeformed geometry and an objective function for a desired target under the coupled response. The typical design variables are parameters to control the wet surface shapes through freeform deformation boxes, or we can also consider structural material properties as design variables. Using the baseline design as the initial guess, we do a direct analysis of this design iteration that is currently driven by C multi-zone driver that exercises the individual solvers and facilitates the transfer of information at the interface. Then we do the adjoint analysis of this problem using C discrete multi-zone driver to obtain the sensitivities which informs a better guess, hopefully for the next optimization iteration. And this continues until convergence to provide the optimized design. The dynamic FSI work uses and develops on the native FSI solver in SU2, and the ethos behind this work on dynamic FSI is to facilitate accurate gradients so that it can either feed into an existing framework, which was originally just a standalone hacked version of the SU2 Python environment to support FSI, or transition easily to the new optimization framework that is currently under development within SU2. In either case, the gradient-based optimization to manage the large design space will be key, and the gradient implementation will leverage on the existing AD-based discrete adjoint solver for static problems. The C-Discrete multi-zone driver, originally implemented by Ole, facilitates the discrete adjoint for any steady multi-zone problem, and this approach has to be maintained for unsteady problems too, so that the final framework will not be exclusive just for FSI. In terms of technical background, I'll start with the primal FSI solver. We have the fluid domain, structural domain, and the mesh domain to consider. For the fluid solver, I've given here the equations for the compressible runs equations in ALE formulation, such that the grid velocities are included in the convective flux calculation to support moving boundary problems as needed for FSI. The viscous fluxes are calculated through FV, which can be set to 0 for unlisted problems. And a quick note here, for FSI, we're not restricted just to compressible flow solver. Together with Tom, we've implemented the ALE formulation in density-based incompressible solver as part of earlier work. Therefore, we can use either solvers for the fluid domain of an FSI problem. The structural domain, we have a finite element-based nonlinear solid mechanics solver implemented by Raven, which is governed by the pointwise equilibrium, and the solution is obtained by a weak form of the equilibrium equations given here in order to find the displacements, velocities, and accelerations to account for the inertial effects as well in the dynamic problem. Finally, the mesh domain is solved using linear elasticity and exists in the code neatly as its own solver, whilst leveraging the necessary methods from the FEA solver. The problem is coupled at the interface through continuity of tractions and displacements, and the overall coupled response is converged using a block Gauss-Seidel routine. For the discrete adjoint solver, it's easiest to explain through an optimization example. So here we have an optimization problem to minimize an objective function j that is averaged over the number of time steps n. We have the state variables u for the structure, and for simplicity here it refers to the vector of structural displacement, velocity, and acceleration. The conservative variables w from the fluid domain, and the mesh variables as z. The design variables are given by A, and the optimization is subject to the satisfaction of the governing equations for the structural, fluid, and mesh domains. The problem is written in fixed-point iterators to allow algorithmic differentiation, and I've included the time dependencies for each of the variables and domains. So for the structure, we use Newmark integration for the time integration, which introduces the dependency on one previous time step, and for the fluid domain, we use a second-order dual time stepping strategy, which introduces the dependency on 2 previous time steps. If we take the Lagrangian of this problem and rearrange the variables in a typical fashion to remove the need to calculate the total derivatives with respect to the state variables, we find the expressions we need for the gradient of the objective function with respect to the design variables, along with the adjoint equations. When the adjoints are written in this form, we can see the similarities to the static equations, with the differences coming from the need for the additional terms in the summation boxes for the time steps, other than the current one. So we have the n plus 1, n plus 2, etc. These come into the equations as source terms, and the calculation of these new source terms require additional recording and extracting from the AD tapes. In order to calculate the adjoint sensitivities, we use Codipack for the algorithmic differentiation, and this is implemented in the code through the use of the new C-Discrete multi-zone driver, and it also has the index tape implementation by Ole, which has been extended for this work, which effectively makes the recording and extracting process much easier and more reliable, as the order of these recordings and extractions are no longer rigid, which helps a lot when there are so many terms. And the point to note is, and the point to note is that this implementation has been done through that driver with no implicit FSI dependencies, so it creates a platform for any unsteady multi-zone adjoints. Moving on to numerical results. Firstly, I want to show a fluid-only problem, but with enforced pitching motion before getting to full FSI. We have here a transonic NACA 12 airfoil at Mach 0.8 with 1.25 degrees angle of attack, and we're just simulating an inviscid flow at this stage. A pitching motion of 17 Hertz with an amplitude of just over 1 degree is enforced. And for this, we have two types of motion that are possible. Rigid motion rotates the whole grid around the airfoil, such that the relationship between each grid points are kept the same. Or we can have a deforming grid, which sets the displacements at the airfoil markers and deforms the grid around it as the airfoil pitches. The deforming grid is a more similar process if the motion was enforced through structural interface rather than user enforced value. So therefore that agreement for this particular type of motion is important before moving to FSI. To check the gradients for this problem, we have an FFD box with 11 control points on each of the lower and upper lines, and we use an objective function of average efficiency. The discrete adjoint results for both types of grid motion are in excellent agreement with each other, and they're in reasonable agreement with the finite differences as well. There are small variations at the trailing edge, but on the whole, the adjoint sensitivities have captured the right trends. Moving this to an FSI problem, the structural component is added and it's clamped at 20% COD, and we use a hyperelastic neo-Hookean material model to in order to support large displacements. The baseline response for this problem is shown here for a stiff airfoil structure, and the angle of attack has been increased to 8 degrees in order to create a strong shock only on the upper surface, which just helps to speed up the coupled response. For the results to follow, we'll use a flexible airfoil with uniform stiffness of 70 megapascal, which is known to be a stiffness level that creates limit cycle oscillations for this problem setup. Again, using efficiency as the objective function, and now with slightly reduced number of design variables, 9 on each of the upper and lower FFD box surfaces, just to reduce the amount of time needed for the finite differences at this stage. The preliminary gradient validation is given here for the dynamic FSI problem, whilst it still operates well inside the linear regime with max displacement below 1% COD. Nonetheless, this is a suitable case for preliminary validation of the dynamic FSI gradients, and from the comparison shown, we can see good agreement is found for all the design variables against finite differences. If this problem was allowed to continue to develop in time, we can explore nonlinear coupled response at limit cycle oscillations influenced by the movement of shocks, but the gradients aren't quite ready for this yet. I think I might need to make a few more changes to the mesh joints to capture the right sensitivities at larger displacements, but I can show the expected primal response for this problem. As the flow develops around the airfoil, the flexible airfoil leads to an upward displacement at the trailing edge that's given by the image in the top right. This resulting shape further accentuates the aerodynamic loading that the structure can't suppress and leads to increased upward displacement that's shown in the bottom left. And the shocks on the upper surface move towards the leading edge, and the strengthened shock on the lower surface leads to a downward trailing edge tip displacement seen in the final image in the bottom right. This in turn leads to an upward displacement of the trailing edge thanks to the now strengthened shock on the upper surface, and so the repetition goes on. These oscillations start out small, but with each cycle, the amplitudes increase until the maximum amplitude is reached for that specific airfoil stiffness and the level of aerodynamic damping in the coupled problem. So to conclude, the work presented is to extend the static FSI shape optimization for dynamic problems. The discrete adjoint method for dynamic FSI has been discussed and implemented in the code using the generic unsteady multi-zone discrete adjoint driver, such that the routines for the calculation of the adjoints are not restricted to FSI. I presented the preliminary gradient validation for dynamic FSI problems with small displacements, and work is ongoing for the extension to problems with geometric nonlinearities. All the implementation is available in the draft pull request number 868, and I hope to have the final implementation merged into develop once ready. The expected future work is to apply the adjoint sensitivities to explore optimal design problems such as the transonic airfoil with the shock-induced oscillations discussed, but also looking at other optimal problems such as a square cylinder with a flexible cantilever beam type problem, which is a typical benchmarking exercise for primal dynamic FSI, and that'll be interesting to extend for design work as well. And I'm also working on gust load alleviation problems using the existing wind gust implementation in SU2, and hope to extend this to optimal design of passive gust load alleviation. That's it from me. Thank you for your time. I'm happy to take any questions.
Great, thank you, Charanya, for a nice talk. So we have time maybe just for one or two quick questions. So if anybody wants to leave a comment in the questions window, please do. I think we have one coming in, so I'll read it out loud. What was the design variable which was optimized here? So what are you using for design variables?
I was using the F50 control points. So I set up the F50 box with either the 22 or the 18, depending on the case. And I was getting the sensitivity to those individual control points.
Great. And then maybe one more quick one. Somebody asks, I would be happy to hear the possible advantages or disadvantages of having the native FSI solver in comparison with passing to an external solver, third-party solver, something like Nastran. So is there any comment you can make in that direction?
So at the moment, I think there's actually quite a lot of work within that code for having these multiple approaches. I have primarily been focused on the native solver. It gives a lot of flexibility for the changes, and being able to automatically differentiate through the code as we're making changes is a particular advantage. But I do believe there's a lot of ongoing work for coupling with external solvers as well.
Yeah, I agree. I think there's been a bit of work coupling to solvers like TAX and a couple other Python-based frameworks. So yeah, we can maybe share a couple links with folks offline. So there are one or two more questions that came in, Charanya. I may pass those along to you, just forward them, and you can look at them offline. But thanks again for your talk. Okay, so now let's transition to the final speaker for the day, last but not least. We have Tommaso, who's going to speak about a couple topics that have come up in the last day or two here, which is radial basis functions and also icing. And this is for in the context of rotorcraft simulation. So Tommaso, the floor is yours.
Thank you, John. And hello, everyone, and welcome to the last talk of today, in which I'm going to talk about radial basis function mesh deformation and its application to icing simulations and rotorcraft simulations. So first, let's introduce mesh deformation in the context of ice accretion and why ice accretion is important. So basically, ice accretion is important because it is unsafe to fly in ice hazardous conditions. And nowadays, every flying aircraft rotorcraft needs to be certified to fly in such conditions. And how do we stimulate this phenomenon? And we use a quasi-steady approximation of the phenomenon, in which we do first the CFD simulation, then we do the particle track into account for the amount of water that is caught by the surfaces, and then we have a thermodynamic model that shows the mass and energy balance on the surface. And the mesh deformation just links together the tail and the head of this diagram here. So after we compute the ice equation, we deform the mesh and we start again with our computations. And some history in mesh deformation. There's a lot of methods to approach this problem. And the oldest one is the spring analogy, which has different, we can have just linear methods, we can add torsional springs, so we can get any kind of deformation that we want. And that's the linear elasticity analogy that was actually already implemented in SU2. And our third option is an interpolation-based approach based on radial basis function. That is what we're going to see now. And so already today we've already talked about radial basis functions, but in the context of interpolating across two surface meshes, so to interface meshes, and the process is kind of the same. We have this basis function phi. They are defined at a given point RE. There are compact support functions, and their compact support is defined with this parameter R here. And we just use this function to approximate our deformation field, and then we solve the problem for the coefficient of our radial basis function expansions, and then we can, after we found the coefficients, we can interpolate our deformation to the volume points. So this system solved here is quite complex because, like this, it's computed on all nodes of the surface, and the sparsity depends on this coefficient R here, and it can be a filled-up system, so it's not easy to solve. So one way to approach the problem is to, instead of using all surface points to approximate the deformation of the surface, we just use a reduced set of points that we can call control points, and to select them we use a greedy procedure in which we start with 1 point, we compute our RBF approximation, we evaluate the error, and we put in our control points the point with the largest error. So this way we can approximately solve our problem up until a given tolerance. And this is still not enough because after a while the number of points that we put in our basis, they become too much to solve with standard direct solvers. And so what we do is we use a multi-level approach that consists in after reaching a given threshold, we deform the mesh, and then we set the error of the previous approximation step to the displacement of the current step. So this is where we start solving another displacement problem in which the displacement is the error of the previous step, and so you can go on, and the basis restarts from a few points every time. So we keep the system small and we solve iteratively the problem. Another way we can use to reduce the cost of the problem is to reduce the extrapolation step to the volume points, and to do so we can we exploit the fact that these functions here have a compact support, and we also use a blending function that is based on a distance to the surface, and so we can just select and displace the points that are at a given distance to the wall. So this distance here to the wall can also be a function of the level that we are deforming. So as the level increases, the maximum deformation gets smaller and smaller. So the number of points that we need to qualify that we may get smaller and smaller. So our some implementation details. So it was pretty straightforward. We just created a new class that inherits from cyclometric movement, and we just override the function set volume deformation, and so we can use the RBF deformation instead of the linear elasticity approach. And then we have all the parameters like the support radius and also the kind of basis function that can be set from the config file. And so it works with a parallel fluid simulations, but the communication costs are pretty high because at every step, so every time that we put a new point inside of our control set, we just need to gather the points from. So we need to search for this point inside of all a different partition in order to avoid weird behavior at the boundary markers. Some results. So we started from to evaluate this radial basis function mesh deformation in an icing approach, in an icing simulations. So here we have our on the left we have our initial mesh, on the right we have the computational and the experimental eye shape with the condition that you can see up here. And here you can see the use of the multi-level approach for RBF mesh deformation applied to that case. You see for different levels, we start by putting points in our base, then deforming the mesh, and then after 1 order of magnitude reduction of the error, we start again. And so we can decrease our error up until a relative tolerance to 10 to the minus 7, relative to the maximum displacement, so with itself in the order of centimeters. And here we can see the number of points that are selected at different levels, and you can see that the points are selected right where the ISAC reads, and this is a wanted behavior, so we can just select the points that are important for our deformation that we want to achieve. And in the next slide, we can see some, this is the orthogonality of the dual control volume. So we can see that the initial mesh wasn't very orthogonal to start with, but after the deformation, the initial orthogonality is more or less constant, is kept in the mesh, with the except of these 2 points here, but that is due to the shape of the eyes. And in this case, most of these kind of eyes cases, they require a remeshing or some sort of mesh adaptation. You can see also, here we can see this is the case that I just presented. Here is a different case which I'm calling global deformation, because the deformation is not concentrated at the leading edge, but is global, and we can see that the convergence of the multi-level procedure is much faster. So at each level, it requires a much smaller number of points to reach a decrease of the error. Similar thing can be done in 3D. Here we have a 3D execution case, and in this case, the number of points required to reduce the error is quite high. So here we just have 2 levels, but it requires more than 2,000 points to reduce the error. And this is still due to the very regular shape of the eyes. You can see it. So here those are the set of points that are used for the deformations. They are concentrated on the leading edge. And here you can see the difference between, on the left, here is the case that I just presented. Instead, here is the global deformation. This is an Oneraim 6-wing with just a flapping motion. And for a regular deformation, we can see that the method converges much quicker and gives good accuracy. So the field that you see here is the error between the RBF approximation and the actual displacement that we're imposing. So since we were having good results for FSI type deformations, we applied our RBF mesh deformation in a rotorcraft simulation. Here you can see the case of a forward flight with the prescribed blade kinematics, and we use a sliding mesh for the rotation around the hub, and we use mesh deformation to model the flapping, pitching, and lead-lagging movement. And here you can see this is a 2-blade rotor at different azimuthal angles. And here, I don't know if you can see it very clearly, but in black you have the control points for different levels. So here for a level of the order of 10 to the minus 4, this is still the relative error. You can see that we can achieve that with just a few points on the blades, and it scales very well to reach an error of 10 to the minus 6 with just the control points that you see here. This was the case with more than 30 billion elements, and so it was a nice result for us. In the next slide, you can see the actual error for different for the different levels. And we converge pretty quickly. And to conclude, we just presented a first implementation of the RBF mesh deformation in SU2. If folks want to contribute to test it, we can we can push a branch, and then we are interested in do a more thorough investigation for for RBF mesh deformation for icing. For instance, we want to investigate the influence of the support radius on the approximation of the deformation, and also the use of different radial basis functions. That's it. And if you have any questions, I can answer.
Okay, thank you, Tommaso. Yes, you do have some questions. So why don't we start here? I'll read them out loud to you. So somebody says, what RBF function is used to Gaussian, cubic, etc.?
Okay, so here for the results I presented, those were Wendland SU2 basis functions. So they are compact support basis functions. But from the config file, you can select also the other Wendland basis function. We also have QRD ones. We also reused some of those that were already defined in the interpolation classes. So all they were defined there, you can use for, you can test for mesh deformation also.
Okay, great. And then another person asks, is there any special smoothing function that's been applied to maintain quality during the mesh deformation?
No, in the results here, we didn't. We were more interested in testing the reduction schemes for the selection of the points rather than the quality of the mesh. So no, we didn't apply any constraint on the quality. The only thing that we used that blending function to restrict the volume points, but nothing for the quality.
Okay, and then another one that actually has been asked a couple times, I think it's a very relevant question, is are the RBF functions that you've been developing, are they available for shape optimization problems?
That's a good question. So for now, we're just using that in moving boundary simulation for single and multi-zone problem, but I haven't tested. So I haven't done any optimization ever in my career, so I've never tried.
We can help you with that. I think people are interested, so it's a great feature. I think it would be great if we could integrate it along with all the optimization capabilities. So maybe a last question from me personally is, what are your plans for kind of merging this or submitting it to the main repository?
I think now they're on a local branch on either mine or Miles' computer, so we would need to push the branch and then we can work on a PR.
Great. Yeah, I would encourage you to do so. I think a lot of people are interested in this work. So thanks again for a great presentation. And at this point, we said we would stop at about 10:25. So why don't we adjourn here for the day? So thanks again to all the speakers for another really great day of presentations. I'll remind everyone that we have a third day coming. So tomorrow, again, 7 a.m. PDT, and we're going to start off with a discussion of ongoing developments and also just open discussion for about 45 minutes. So we'll probably do like we did on the first day at the end and have some of the panelists on answering questions. And we have a small slide set that we'll use to kind of seed the discussion. And then after that, we have a full day of more exciting talks. So I hope that everybody can join here again tomorrow. Same story, you have the link, see the conference page for the slides and whatnot. And we'll see you tomorrow at 7 a.m. Pacific, okay? So thanks, everyone.
Thank you very much. Goodbye.
Thank you all.
Thank you. Bye.